All right. Sorry about that. We're having some technical difficulties. So two things. One, I'll be summarizing the AF5 report. Because of a screw up on my part, there was a talk that wasn't scheduled. So Richard Tallman's going to get a few minutes to talk about an EDM at the end of this. So we're going to do my report, have discussion, and then he's going to present a short talk on the on an EDM experiment. Okay, so I'm presenting the report for the AF5, which is accelerators for physics beyond colliders and rare processes. The group was myself, Mike Lamont at CERN, Richard Milner at MIT, or may not be out there in Radioland. I am not clicking. The clicker is not working again. Yeah. Okay. Oh, the cursor? Oh, you mean this? No, that's a laser. Oh, okay, I see. Okay. All right, so the outline, I'm going to go over the mission of the working group. Okay. Yep. Okay, great. Fingers crossed. All right. So I'm going to talk about the mission, the areas of physics interest to this group, an overview of the process, what we went through. Just I'm going to list some of the contributed LOIs and contributed white papers, and the outline of the report itself. So the description was, this is just the mission from the page, is that it requires physics accelerator related issues related to rare processes. These are things that are very broad and complementary to searches at colliders. So these are things that aren't at the intensity frontier or energy frontier, but are complementary. First thing you know is that's a very broad mandate, and wrestling with what exactly we were supposed to do is actually a big part of the process. I'm going to talk about them. Yeah. So I want to point out that this actually benefited greatly from the physics beyond collider study at CERN. That was sort of our roadmap. That was a big study in 2016 and was reported to the, Mike Lamont was on that. So this was actually a big help in getting started, and that can be found at that link. So some of the things, this is low energy hidden sector searches. These are motivated by Axion as well as astrophysical hints. The energy sector, these are some of the example experiments. So helioscopes like IAXO or baby IXO, haloscopes using resonant cavities. So again, some of that we consider our mandate to include the accelerator technology involved. Light shining through walls like Jura stacks, that usually involves very powerful magnets. So that also involves other accelerator technology. And so these are areas where this is synergistic research with other groups. Light dark matter search is a big part of it. These are direct WIMP searches. Those are cosmic frontier. That's not accelerator, but the others fall into mostly beam dump experiments. And this is a huge range of experiments from BDF ship, Sequest, NA62 mini boon, electron dump experiments, NA64 LDMX, BDX, use of novel facilities. These are also things, the electron beams, that could potentially be an early use of Wakefield accelerators, and then long-lived particles at colliders. Not all of these will fall into a report. I'm just sort of listing what physics falls into the report. And then finally, precision measurements, things like the muon sector, mu to E gamma, things like that. Rare kaon sector has always been a very profitable way to study physics, or very performative way to study physics. Then precision measurements, things like G-2, of course, is in the news a lot. Permanent EDM, so protons and deuterons, or strange charm baryons, that's other areas, and those experiments often have unique accelerator physics challenges in designing the storage rings they use, things that aren't automatically addressed by the more mainstream thrusts of the physics frontiers. Technologies, of course, cut across these. So in addition to the accelerators themselves, the novel accelerator physics problems faced by these experiments, they do involve technologies. They involve high-speed magnets for things like Axion and dark matter searches, but they're usually very different than the magnets that you would design for an accelerator. Superconducting RF, that's typically Axion searches, and certain other particles involve very high Q tuned cavities to look for these interactions. Energy recovery Linux, some of these things would drive, for example, beam dump experiments. Induction Linux, actually, that's kind of a side issue I'll just mention in passing in this particular context. And some of the technology used as sensors, the instrumentation group. We really didn't talk about that. We may add something to the report. And you know, a lot of these technologies go into things that aren't necessarily accelerator based, but they couple the two areas. So I just want to say at the very beginning, we've posted a draft report, and it's definitely still needs some work. So I would encourage people interested to read it, point out some of the things we've invariably left, you know, unquestionably left out. Don't bother telling us about typos yet. Let's go through one more round, add material, edit the content, and then there'll be a draft where I'll say, okay, now you can tell me about typos. I would just be swamped with typos at this point, I'm sure. So again, I encourage feedback. This has now been linked at that link. So, you know, we kind of, again, this is when you compare it to the other frontiers, this one is very broad. And so we really struggled with, you know, what exactly we included, what exactly we wouldn't include in the report. So we wanted to focus on areas that required accelerator development that wasn't automatically being addressed in the energy or intensity frontiers. And we really won't talk much about experiments that are purely parasitic to other experiments. So things that are parasitic to a neutrino experiment or parasitic to a collider experiment, we didn't see that as our mission. This is just some of our workshops we had. You know, we had brainstorming sessions. We've had a couple of cross-frontier measurements. We had some very productive ones with energy frontier and rare process. That's, of course, the rare process is our main overlap. And then we had a joint technology meeting about targetry issues. You know, we, of course, like everybody else, we took a year, spent a year dormant for COVID. We participated in a beam dump experiment workshop, booster storage ring workshop, muon workshop, and then we've actually worked very closely with the charged lepton flavor violation community. So we've had too many meetings with that group to list. This is just to summarize. I won't go through all of them, but if you look for the LOIs that were submitted to SNOMAS, there were a total of 70. Well, there were 33 that were tagged AF5, and again, you see they're primarily in the dark sector. But some were, you know, they were kind of, you know, they were across the map. We have rare processes, EDM, nuclear, 33. I combed all of the LOIs and I basically identified 41 others that probably should have been tagged AF5. So, you know, these are the list of ones, you know, we have a whole table that we'll probably append or somehow put onto the report, that everything that was sort of related to the AF5 area. So, you know, the first thing you come up again is a lot of these are sort of one-off experiments, and they, you know, they already address the technology in their proposal. So, you know, what can we contribute? So we decided to focus on the development of facilities to serve multiple physics group. And in that context, a lot of our report is actually dedicated to PIP2 and beyond at Fermilab. And yes, that is a Fermi-centric view, but in the US process, that's a big part of what's going to be happening in physics, and that's also a big part of where this process can influence, because that program is still very much up in the air. What's going to happen beyond the focus on LBNF and Dune. Basically highlighting capabilities of various facilities, and in this actually there's quite a bit of overlap with Bob Zwaska, but we're kind of coordinating his targetry group actually has a lot of the same information we have about the beam capabilities of various facilities. So we're kind of coordinating those two efforts. Right now, they're largely duplicated in the two reports. Experiments that require significant or unique accelerator development. So that would be something like an EDM measurement that may have some very stringent and unusual storage ring requirements. And then identify cross-cutting technology. And that would be things like RF, targetry development, and magnets. Within the accelerator frontier, there was a bit of a mix-up, so I wanted to just call this out. Bell 2 kind of fell between the cracks. I thought they were in, or we thought they were in the collider group. The collider group thought they were in us. We kind of forgot about them until they started reaching out to us. So we decided they did belong in AF5, and we've included, we've added them to the report. And we're happy to add more. So I won't go through these in detail, but after the LOIs, these are a list of the, there were actually a few specifically AF5 tagged white papers, and actually some of these were Bell 2, but there were things like, for example, beamed up at the PIP2 LINAC. I just want to, some of these Bell 2 papers. I'll talk a bit about the accumulator ring. This is a very important topic that I'll talk about in some detail in a few slides. Other contributions were related. They weren't necessarily tagged AF5, but they're clearly strongly related. In particular, this was covered actually very well yesterday at the physics opportunities for Fermilab booster replacement, and Matt Toops gave an excellent talk on this one. Red Top is a rare Eta prime experiment. Bell 2, again, there were 2 Bell papers submitted that certainly, they're looking, among other things, for physics beyond the standard model. A lot of white papers. This is a RF rare front tier 2 weak decays of strange light quarks. So kaon, hyperon searches, CP violation, hyperon, rare kaons are still promising searches for physics high intent. So kaons are still very much a part of the future. Axions and EDM, so these again involve rare pion decays, and there were a number of things. This is actually a very excellent overview paper of just what's on the horizon in terms of EDM searches. This is a very comprehensive white paper, so if you want to educate yourself on that area, it's a really good place to start. Charged lepton flavor violation. So this is kind of the bulk of the things related to PIP2. So one is specifically mu to E conversion, but then another one is just called a new charged lepton flavor violation at Fermilab. And this is a fairly comprehensive look of what could be done, at the same time as the LBNF2. So this encompasses the scope of PIP2 as it stands. There's a project that's moving along and has certain goals and certain deliverables, and we have proposals for exploiting those. But then going beyond that, or even augmenting that, there's a lot of things in the mix, and I'm gonna talk about some of those and how they relate to physics. So this is kind of how we outlined the report after an introduction that sort of lays out the physics cases. We think both in terms of our mission and in terms of the context of this particular workshop, that maximum exploitation of PIP2, and I should say PIP2 and beyond, is really important to discuss, because beyond the actual building of PIP2 and supplying beam to LBNF Dune, really nothing is set in stone. This is still very much a situated in flux. So, this is the kind of thing you have to have discussion of. And this brings in a number of very interesting accelerator things having to do with, there's a lot of power that will come out of PIP2, and I'll talk about that in some detail, but the bunch structure that needed by most experiments does not naturally come out of PIP2. So that you have to do something to create the bunch structures needed by experiments, and that there's many solutions being proposed, and they have competing priorities, and that's something that we said. And Bill Pellico actually yesterday gave a very nice talk on that. Beam dump opportunities. This is kind of a clearinghouse. The physics cases for beam dumps are broad. Basically, anywhere you have an intense beam, you can make a beam dump. So we have tabulated it in the report particularly, and a lot of this also came out of the European report. So a lot of the physics is outlined in the report. Mike did most of that. And again, we're kind of working with Bob, who did a nice tabulation of facilities. And then the other things are we just kind of list experiments. Bell 2, EDM measurements, rare kaon. These are things where we just go through experiments that don't kind of group into one thing, but Richard contributed a bunch to this, but again, Bell 2, EDM measurements, rare kaon measurements, and then just identified synergistic opportunities with other working groups. Not a lot of detail in that section, but just like these are the areas where we think we should be talking to these groups and make sure, some of the needs of target development are in common with target development for muon colliders or neutrino factories, but there may be different things. So I'll talk a little more about that. RF magnet development. Again, commonality, but very, very different, particularly things like magnets, very, very different parameters for something you would make for, say, a shining through walls experiment. So I'm going to say a few slides about PIP2. I'm sure everybody's been hearing about them, so I'll go through quickly. But just to remind you, the main goal of PIP2 is to replace the LINAC, which is half original at Fermilab, from 400 to 800 MeV. Because of the strong dependence of space charge on energy, that and a more sophisticated injection technique will allow much more beam to be accelerated by the existing booster. So it'll still be existing booster, which is the only original thing at Fermilab still left. And that the goal is to deliver more beam to LBNF Dune. That's the motivation for the project. But that will only use a small fraction of the beam provided by that. And so there's going to be lots of excess beam to deliver that could support other experiments. And really not using it would be a real waste of the capability. So again, I keep harping on this point. This is something where, you know, some of this stuff runs on rails, you know, the LHC upgrades, PIP2, all this stuff has already left the station, but these are areas where, you know, they're still very much in a state of flux, and, you know, we want to make sure we serve as many people as possible. So just, again, this is, I won't, you know, the PIP2 LINAC is to upgrade to 800 MeV H minus, 2 milliwatt CW, so that's 1.6 megawatts of potential beam power at 800 MeV. Upgrade the booster, that's a little bit of details. These are things, but again, this is the important thing. The PIP2 supplying all the beam that LBNF can use at this point is 1% of its capability. So, you know, using the beam, splitting the beam could provide leave a lot of beam to other users. A bit of subtlety. So one of the you know, is how you would share the beam. So this is one of the things that's not part of the scope of PIP2, but we've been discussing it, is how, you know, how you would switch beam. So, you know, you could switch it going to the booster or going to something else, or you could use what's called an RF deflector to switch it to other experiments. So one of the features that's very attractive about PIP2 in supporting experiments is it's got a completely arbitrary beam bunch structure up to a maximum of 162.5 megahertz. So you can make you can type out Morse code, whatever you want with bunches, and send them. So if you have an RF deflector, you can select beam lines by which bunches you populate. So the two antinodes would get a maximum of 40 megahertz, and the node line would get a maximum of 80. But of course, you can then create, subject to these limitations, any bunch structure you want within those things. So, you know, just as an example, because this experiment has done the most work, is, you know, there is a proposal to send beam directly to the mu-to-E experiment, which needs a bunch structure of sort of, you know, 1 to 200 nanosecond pulses separated by 1.6 to 1.7 microseconds. And this can be done directly from the PIP2 LINAC by just properly populating the bunches in one of those lines. And this just shows how it's done. And again, just to show, this would be roughly 10 times the energy in the first stage of mu-to-E. So, you know, just by using beam directly from PIP2, you can do a lot of technical challenges there, but the beam is not a particular challenge. And going to a higher power would simply mean doubling these bunch widths. So, you know, this experiment. Beyond PIP2, now this actually, this applies to some other experiments too, but going beyond mu-to-E2, basically you need something to make the beam, basically get rid of all the pion backgrounds without waiting. And you also want something to more monochromatize the beam, make it more monoenergetic. And most ideas involve an FFA of some sort. This would be like the Prism Prime proposal at JPark. And the problem with that is you cannot, what you need is short, you need basically 10 nanosecond pulses, very intense at 100 to 1,000 kilohertz, and you cannot power this directly from PIP2. Likewise, most beam dump experiments would rather have a narrower bunch than what you could make by just shipping a lot of PIP2 beam to them. So both of these things lead to things beyond the scope of PIP2 that involve some sort of compressor on the beam. Now, I wanted to point out two competing priorities. One priority is to have a preloader that you can load beam into to inject it very quickly into the booster, because the existing booster runs in a resonant circuit. So you're essentially injecting beam into a movable target, and right now this is actually flattened when you inject the beam. But if you start to inject more beam, this gets longer and it becomes impractical. So this is the proposal that's just called they've changed the name, proton accumulator ring, I think it's called now. But the constraint here is it has to have the same period as the booster. Again, Bill Pellico, they've got a very mature proposal for this, or a fairly mature preconceptual design for this. This is kind of at odds with the basically, for the other things, we want to get as many beam particles in the accumulator ring as possible. And that basically that space charge problems scale with the circumference of the ring. So for that, you want to make the smallest. So this goal constrains the ring to have the same period as the booster, which is about 1.6 microseconds. For the other things where they say we want to put as much beam into the ring as possible, you want to make the ring as small as possible. And so that's a competing priority. And these also need bunch structures that, this is a fill and extract thing, just like they do now with the recycler at Fermilab into the main injector. You fill the ring, then you transfer it to the booster. And the other experiments usually want a very different bunch structure. So you had a much more complex sort of injection and extraction scheme. So we're having discussions about how we can do a preliminary version of this with this design, because we don't want to wait forever for the others. But ultimately, to reach the ultimate energies, you probably need a different design. Just some of the other things. This is just a list. A lot of this comes actually from Matt Toops's thing. So Matt Toops again gave a very good talk yesterday. I just pulled this from it. That physics opportunity, he said, for a booster replacement, but a lot of these are PIP2 and a booster replacement. They're just things you can do with lots and lots of low energy protons. Some involve slow muons. He references muonium. We did a white paper, and it's listed in the paper a few years ago, about just a general slow muon program from PIP2. So that's not high energy physics, but it could be. There are no facilities in the US that can support the thing. So PIP2, even without any modifications, could be fully competitive with Triumph and PSI, which have fully subscribed slow muon programs. PSI is a continuous beam from a cyclotron. ISIS is a pulsed beam from a synchrotron. And so, and there's lots of people in the US who are interested in this physics, and we think there would be. So you can basically be fully competitive with these. So these are things, it's not high energy physics, but there's a community that's interested, and it could be done, in conjunction with other experiments. Again, I think at this group, in the context of snowmass, an important thing is to, discuss potential users. I've been talking to well, I was talking to Leah before, but we haven't really, there hasn't really been a users community coalesce around PIP2 and beyond in a way that we can come up with a coherent plan. And then these are, how to proceed. I think most of us, we don't want the better to be the enemy of the good here. So we would rather figure out how we could use an intermediate compressor ring solution to make incremental improvements in measurements, rather than just hold out for something that may or may not ever be built, or might be built when we're retired or dead. So beam dump experiments, again, this is a pretty thorough chapter. A lot of it is kind of cribbed from the European report. Just basically breaks down, beam dump experiments are broadly sensitive to the dark sector and other rare processes. They fall into two proposed groups, proton and electron. And this is just a list. I don't expect you to absorb it all, but you see there's interest in from very low to very high energy protons. And these are some combination of ongoing or proposed experiments. And they're looking for light dark, basically they're looking for light dark matter or dark photons, basically dark sector stuff. Some are specifically looking for sterile neutrinos. And so some of these are, again, there's overlap with the neutrino frontier for a lot of these things. And again, we didn't list ones that are fully parasitic to neutrino experiments, but this is just the the range of energies. Very and again, there are a couple of very nice. There are two separate papers by. Well, Matt was the primary author, but there are two separate papers about, and these are Fermilab specific, but very nice physics cases for what you would do with a 1 GeV program or a 10 GeV program. Here are some of the proposed electron beamed up experiments. And there's actually, I think I left off the Slack one. Sorry, we'll get that, I can fix that. But basically, again, a wide range of energies, tens of MeV up to multiple GeV. This is also an area where, I personally think it'll be a long time before something like a Wakefield accelerator is able to, contribute to the energy frontier. But one could imagine, an early application being of some sort of Wakefield accelerator being an intense, where you really don't care about the beam parameters at all. You just want energy and intensity. One could imagine that be a compact Wakefield accelerator somehow contributing to this field. Yes. Yes. Yeah. I just listed the energy. That's just meant to emphasize that. Yeah, I should have said that. Thanks for that. There's really very few beamed up experiments where the energy is important at all. It's just beam power, which is also true of muon experiments. Beyond, even neutrino. Most of these experiments, it's the beam power that. This one again, not I had to shrink it so it would fit here, but. Look in the paper, and whatever we've left out, let us know. And again, I'm coordinating with Bob Zwaska on this because he has a very similar table in his targetry report. So EDM measurements, and we'll have an example talk after mine. They typically involve unique storage ring designs, including some that involve electrostatic storage rings, which present very interesting accelerator physics topics. So this is just one example from a talk by Yana Simertidis. Let's see that at a conference I wasn't. I certainly didn't copy this slide from another talk. But this is I'm sure he actually has given a talk somewhere in this conference on this thing. But basically it's a very similar technique to anomalous G-2 measurements, where you're looking for something which, if there were no EDM, you would not see a precession, and you see a precession. Everything's a variation of this, but like the G-2 experiment, they typically have extremely stringent requirements on the storage ring. Bell 2, again, they just to show you that since Babar shut off, they are the they're the show in terms of intense C+ E- beams, and of course they have an asymmetric beam to do time-dependent CP violation oscillations, but they're also just their goal is to ultimately reach 610 to the 35 per square centimeter per second. And if you're running on a resonance, just like at LEP or any experiments running on resonance, you just get lots and lots of events to study all sorts of rare processes. So this, of course, it's high current electron beams, and the challenges have a lot of overlap with other high current machines, high current storage rings. So those are the challenges. So this Tom Browder asked me to announce this at an earlier meeting, but they're forming a working group to improve luminosity. So this is something that's of general interest to electron accelerator people, including even from the synchrotron light source community. Anybody who works with electron machines, in particular circular electron machines, we're interested. But again, their goal is this: they've broken records, but they're still sort of an order of magnitude away from that. So they're still they've broken all the records for E+ E- luminosity, but there's still a lot of exciting work to do there. So the final section of the paper has to do with synergies with other working groups, and that's in particular, most of the technologies in the area are in AF7, which is the technology area of the accelerator frontier, and those divide into targets. we had a joint workshop. So target development for the neutrino muon colliders can certainly benefit beamed up experiments. So, there's the materials themselves, how much beam can you put on a target, how to cool it, what would be damaged, but also, you can certainly imagine beamed up experiments that would benefit from the sort of highly radiation hard detector technology that's being developed for the neutrino sector. Well, and even there's some overlap even with the collider community here that, if you imagine, one of the things they're doing in the neutrino sector and beyond is, designing detectors that can survive just withering radiation environments. And that's something you could imagine making a smart detector of some sort that would, or a smart target that would augment you. Look for offset vertices, things like that, locally. High field magnets, both the axion dark matter searches, typically involve very high magnetic fields. The light through walls experiments involve, essentially a dark photon coupling to a very high magnetic field and converting to a visible photon. And these typically involve, the higher the magnetic field, the better, but they typically want larger apertures than, they're not interested in small aperture magnets like you would have in a accelerator, dipole or quadrupole. But the technological overlap, the mechanical design issues, things like that, there's some synergy there. RF is mostly axion searches with some others, but axion searches are the ones that typically, rely on tunable high Q cavities to search for axions. And there's certainly communications to be had there with the general RF community that's mostly being driven by either highest gradients or unique compact RF designs for other applications like crab cavities or spoke resonator cavities, things like that, deflector cavities. And so, I think, there's a place where there's a lot of overlap. So the conclusion of the report is lots of interesting physics out there. I think snowmass should play a key role in all of it. But again, I keep focusing on, I think the big area where there's potential uncertainty is in the evolving Fermilab program in the high energy physics area. Very important to keep track of all the capabilities of the lab. Again, we should keep in mind the synergy with the other R&D areas. So at this point, I intentionally kept this talk short because I'm fundamentally lazy, but also because I think we should have some discussion. I will definitely, whatever people say, I'll go back and listen to the recording and we'll try to incorporate it into the report. So. Yes.
Waiting for the microphone. Oh, sorry.
Sergey. Okay.
So, Eric, first, I think that the point that you've brought, that the DPF community has not coalesced around PIP2 is a point that needs to be elevated to the highest level of snow mass. This has to come through, being on the advisory or whatever, the panel of the snow mass organization, I've brought this topic to, already repeatedly, that the previous snow mass and the P5 made the decision to build $1 billion capability at Fermilab with no users other than 1% of beam.
Mm-hmm.
We are going to spend another $1 billion on upgrading it. And if there are no users, this really looks unfortunate. And so far in the snow mass, I've seen that there are people who are interested in neutrinos. There are people who are interested in, energy frontier. And there has been zero talk, really, literally, about how to use a $1 billion class PIP2 capability that provides 1.6 megawatts potentially. So, I don't know how else this, I think, needs to be elevated through the AF report all the way up to the snow mass, because if we have to wait for P5 to speak about how to use this, it means that, you know, we will have to delay the upgrades of PIP2 to you know, the next stage until the P5 speaks up, and you know, until the next coalescing. Is that, I mean, that's how I feel about
I
it.
obviously strongly agree with that. That's why we elevated, we elevated it to a.
But this is hidden in your some group. It needs to come up, you know, all the way to Joel Butler or whoever
Joel's
is
mad at me
running
right
this.
now for screwing up the talk, but when he calms down, I'll. But yeah, no, I obviously agree, and I personally want to. I personally want to start pursuing that. I mean, we've reached out to, you know, I reached out to Leah about this thing but you know, she was, you know, they're very busy.
Okay, but so
But
Leah,
yeah,
of course.
I obviously agree, and we'll do our best to elevate this up to the highest level.
So the DPF needs to come to grips that we've built a facility for them, which they are not using.
No, that's
Or we are
point.
about to build the facility, right? This is that's,
yeah, no, I mean, no, I obviously, like I said, we quickly identified that as one of the big questions.
So the second comment or question is, Fermilab now has the Muon campus, which involves the recycler for debunching, which follows the target, of course. Then there is then there is a ring and 2 buildings with G-2 and Mu2E.
Right.
I would think that this is a very attractive infrastructure to do experiments. You know, after the G-2, you can reuse the building for kaons, for example, or for some other things, which we can do slow extraction with. So I'm curious how, I mean, and instead we are showing beam being sent from PIP2 to the Mu2E, which I think is a non-starter because everything in the Mu2E right now is designed for 7 kilowatts of beam. I don't even know if it's possible to upgrade the present. So I'm saying that the Muon program with PIP2 is not going to happen in the Mu2E building. In the existing Mu2E, it's going to be off to the side.
Well, your comment about kaons, that's a good point, and we'll need to look into it. I mean, Mu2E2 is, I mean, it's a pretty mature. I mean, there is a plan for running 100 kilowatts of beam to the experiment. I mean, the radiations have been, studies have been done. The biggest issue, I don't want to derail this, but the biggest issue is beam goes in a different direction at 800 MeV. But the radiation issues, the targetry issues, those are being addressed, and it's a there's a white paper submitted. I was pretty close to that process, so that's at least, I mean, nobody's just saying we're going to send 800 MeV to Mu2E. That yeah. So, but your other point about the kaons, that's a very good point. We should probably engage that community for.
Okay.
Okay. I think we've got one in the room, and then we'll do 2 on. Go ahead.
Yeah, so this was a follow-up a bit on the PIP2. So you have seen that there is a strong community now that are very interested.
Excuse me, could you talk without your mouth? I really can't understand you.
So you have seen that there is a strong community that is now interested in muon colliders and try to see if this could be something for the future. What can PIP2 do for eventually a muon collider, or does it have to be modified? Or
Obviously a lot. Yeah, and I think that's actually an area of the just because there's a muon collider group, separate working group. I haven't put much language in the report yet, but yeah, obviously there's huge. The PIP2 can contribute to muon collider development at every level. Yeah, no, that's a big overlap there.
Thank you.
Oh, you want to go to the online? Oh.
Scott, do you hear us?
Yeah. So I realize you kind of said this wasn't your job, but I'm about to suggest that maybe it should become part of your job. So, you know, I sat in on another session yesterday talking about dark matter candidates and such. They had quite a variety of parasitic experiments that they wanted to do, but they weren't doing. And as an accelerator person, I say, well, why the heck aren't you doing them, right? Because like detectors are free, I suppose, right? Which of course is not true, right? I mean, there's some reason that, and presumably it is cost, that existing facilities are not being fully, or existing possibilities, I should say, is probably the best way to put it, are not being fully utilized. So I guess I'm suggesting that maybe we need some discussion or coordination or whatever between the accelerator and of many of these experiments and the experimental and to try to strike the right balance. And I think this goes to Sergey's comment as well, in the sense that you have PIP2, let's start utilizing it, right? Fully utilizing its possibilities. And so yeah, I think we need to figure out how to strike that balance between, hey, I've got this great new accelerator idea versus fully utilizing what we have. Thank you.
Right. That's a really good point. I maybe saying it wasn't my job, wasn't how I intended to come across, but let me be clear. We actually raise a good point, and that's really at the heart of our mission of cataloging accelerator community capabilities and advertising them to the dark matter community. So you say, people don't, we find this in other areas. People don't use particular test beams or radiation facilities because they just don't know they exist. And I know that group is putting out a white paper. But same thing, we're cataloging we're trying to catalog the abilities, since there is a rare process group, discussing the physics is going to be done. We saw that as being more their thing. Our thing, we're saying what's specifically accelerator related about supporting these experiments. So I need to do something that's different for them. That's specifically the accelerator. If the accelerator is being built for a neutrino experiment or a collider, then I didn't see that falling specifically into our group, but saying those things exist and possibly in addition to our beam parameters, give specific, we could augment our table, thinking about your comments, we could augment our table to just saying what's going to exist at, for example, neutrino experiments, like, what's going to exist at LBNF, that if you wanted to make a parasitic experiment, you could just sit there, or, what a potential a parasitic experiment at an LHC detector might be. So that's actually, I think that's a good point, and we can add that to our capabilities section.
Well, I think it's more than that, actually. I think in many cases they know these things exist and they want to use them, and they are not. And admittedly, I did not go ask the question there, why were they not? They're actually saying, we want to do this. We've got these dozen things that we want to do, but we're not doing them. And again, the only thing, my guess is that it's because they don't have the funding. So I guess what I'm saying is it's searching out that right balance in funding so that we do fully utilize what we have.
I think that's a good point. We can certainly put in some words in our report about that, we can say things like there are lots of physics opportunities and they should be supported, and often they're bargains, and both in terms of cost and time scale compared to other things. But obviously we're not the people to make the physics case for it. So I think the physics case has to come from that community. But I think you do make a.
Yeah, I think it's a matter of getting maybe sitting down with the right representatives from that community, figuring out what the underlying cause really is, and seeing if we can come up with a common statement in some sense.
And we're certainly happy to take part in such a process. I don't think we're the right people to lead that process.
Oh, fair enough, but I'm not sure to what extent
You want to do the other on? I think the other, there's a sec. Was there a second online question? Oh,
Yeah.
hey, Bill.
Hi, Eric. In your list of your complete list of world's beam dump opportunities, of course, it was too small for me to see with my ancient eyes, but I don't think you had Euro-XFEL there. And in particular, you didn't discuss the opportunities of the free electron lasers at the highest, running at the highest energies, which are LCLS1, and more so even Euro-XFEL, to do strong field tests of quantum electrodynamics. There is such an experiment planned. Almost certainly it goes forward at Euro-XFEL, and those are things our community, the accelerator community, ought to know about. Another thing is, I know that lasers don't accelerate photons, but they are such an integral part of our experimental capabilities that somehow we should just say, we should just adopt them into one of the technology groups, like you do with superconducting magnets and superconducting RF. Certain classes of lasers ought to be mentioned as an enabling technology. But then I want to finally comment about the class of underutilized opportunities. Money is very tight, and primarily due to the cost overruns in big experiments. It's not our job to provide the science case, and unless users make a strong science case and sell those through the snowmass process, there isn't going to be an opportunity to utilize underutilized experiments. Now, what we can do is make a compendium, and it should be short, and it should be highly descriptive of capabilities that exist that could be used for a class of experiments. Then it's up to the experimental physicists or the theoreticians to make that case. We can't do that for them. That just looks very self-serving. That's, you know, I'm not saying we don't use them. We ought to use them, but I think we have to be careful how we make that case. And it really needs to be done in the over a beer conversation with the conveners from the experimental physics groups.
Yeah. Okay. So to your FEL point, very good. That was actually an oversight at this point. We fully intend to put that in. It just got right. Yeah, that fully intend to put that in. The laser, that is a very good comment. That one. Yeah. And in fact, you know, every time somebody claims to be the first group to create E+ E- pairs from light, I always have to send a letter to the editor that we did it at SLAC in 1996.
Exactly.
But yeah, very good point. Yeah, as far as the capability, that we seem to keep coming back to that. I know, for example, CERN keeps a database of like test beam facilities and radiation effects facilities, and you know, maybe we need something equivalent for this. Okay, next in real life question.
You mentioned this.
I don't think, are you live?
Can you hear me?
Okay. Yeah.
I think it's fine. Yeah. You mentioned this super KKB. They just recently formed the international, task force try to increase luminosity, which is factor of 10 away. My question is, it's to make a real impact to the project. We probably some funding is necessary. The question to you is, do you have in your listing, is that a possibility there? Or
Again, I don't think we're the people to make that case. I mean, again, this is the accelerator frontier. So that's a case that has to be based entirely on the physics.
It's not, I'm talking about improve accelerator.
I see what you're saying.
One of the reasons super KKB it's important because there are lots of physics like beam or beam dynamics.
Okay, that's
actually push the frontier, which is very important for the next generation say Higgs factory.
That's a very good point.
So,
and
it's
actually,
not like just, help others. It's not actually true. Otherwise, I will not mention it.
yeah, actually, I kind of say that's a very good point. Yeah, I think
So
we say words to that effect. I mean, that's kind of why we included, that's why we first initially didn't include it in our group, and then we determined it should be in our group for
it's one of the
exactly that
issues.
reason.
Maybe not higher priority, but
Right,
it's-
but no, I think articulating the
Yeah.
generic accelerator
that's right.
development
It's
is actually a very,
partially related.
yeah, I
to
mean,
in physics
they
and
discovered,
frontier.
they discovered electron cloud, right? Or they and Babar, that's a lot of stuff was, a lot of very important accelerator physics has been driven by the B factors.
That's right.
Yeah.
Actually, they are on
A lot of
frontier.
the beam effects.
Some people even say they are
grab
the test,
cavities,
they are
all
the
those
test
things
bed
were,
of the next
all those
generation.
things were pioneered for the B factors.
Thank you.
All right. Hi, Erica. And this is Bob Zwaska for the people on the phone. Just a few comments and then I think kind of a problem statement. So first of all, my group is accelerators for neutrinos.
Yeah.
So that's where a lot of my effort is.
Right.
There's a separate target technology group.
Yeah, and I remember I put you with, put you
Okay.
in the wrong group.
All right, good. So yeah, Charlotte and Frederic and others are putting that together.
Yeah, it's what's her name? Who are the people that?
It's Charlotte Barbier, Frederic
Yeah,
Pellemon,
right. Sorry,
and Minnie
that
Sun.
was a slip on my part.
Okay. So my perspective though will come mostly from the AF2, the accelerators for neutrinos. But first, I want to point out we were discussing, these experiments as maybe parasitic, and just as someone who actually does work in the target space, I don't think we have any parasitic experiments anymore for the most part. Once you start talking about several kilowatts or tens of kilowatts of beam power, it becomes a very substantial facility. So every one of these experiments that are proposed has to have some kind of substantial target facility, experimental facility, whatever you want to talk about it as. And perhaps those aren't being explored out at this point. But I just encourage people to look at what J-Park built with the Hadron Hall there, which is a roughly 100 kilowatt, maybe it was originally capable of more, but 100 kilowatt facility for several different experiments, and it's bigger than this room, right? It's a very large facility.
Yeah.
So I think we need to keep that in mind, that we can't do 20 experiments on PIP2. Now from the accelerator point of view, and I'm going to kind of rephrase what Sergey said here, and because I think it's a little bit different, is that we built PIP2 or building PIP2 to achieve 1.2 megawatts for the neutrino experiment for LBNF. And that's really the purpose. Okay. And at the same time, we want to know what else we can do with it. Okay. So we have a purpose for LBNF, 1.2 and LBNF 2.4. We're going to go to work on successors with the goal of having something available in the middle of the next decade. And so things are going to go, relatively fast in making design decisions for what the PIP2 successors are. And I think if we look back, there were design decisions made with PIP2, which were perhaps not optimal for, some of your experiments, the neutrino experiments. And so we're going to get into a situation in the very near future where we're going to be making these design decisions on how to get to 2.4 megawatts. And, we saw yesterday, there's a lot of different ways to do it.
Yeah.
And
That's a good point. And as I was going through my talk, I realized I actually left out a slide or two, and it had to do with that issue of beyond the booster. It's in the paper.
right.
There's a section in the paper that specifically talks about beyond the booster, the things we talked about yesterday. And long story short, I really thought it was in there, but long story, I may put it in and upload a better version. But basically, long story short, the PIP2 is very well defined. But that only gets to 1.2 megawatts to LBNF. LBNF or Dune wants 2.4. Well, they want way more, but 2.4 is the realistic number. There isn't a plan to do that. There are many proposals to do that, and they all of them involve replacing the booster, which, since I used to be in charge of the booster, I remind is the only original piece of hardware at Fermilab, or the only original accelerator. It's almost 60 years old, or over 50 years old. So, that's going to be replaced. Is it going to be a LINAC all the way to the main injector? Is it going to be increased energy LINAC plus a rapid cycling synchrotron? What will it take to support other experiments at either of those energies, a higher energy LINAC or the output of a rapid cycling synchrotron? Do you need the recycler? Is there an intermediate step? Sergey presented a plan for, physics opportunities with a lower cost thing that still uses the recycler. So, getting to the 2.4 megawatts, that does not have a plan. It has lots of proposals. And when we think about, as Bob just said, the focus is going to be how do we get 2.4 megawatts to LBNF, but we should be thinking about what else can we support when we do that. So that's a really good point. It will definitely beef up that language.
I mean, Bob, thanks for, of course, I mean, I appreciate what you're saying. I'm just saying that how do we make a decision of how to proceed with PIP2 upgrades? I mean, if it's just 2.4 megawatts, okay, well, then I would say, it's then we shouldn't wait for the rare processes to coalesce. But if we have to wait for them to coalesce, that means that we will have to wait for the end of P5.
Good
Is
point.
that the timeline?
Right. I mean, that's kind of the question. Yeah. So with P5, we have to have a feeling coming out of this of
Right.
do we
so-
need 5 megawatts at 1 GV, or do we need 2 megawatts at 8 GV? What do we need? And I don't think, I think some things have become more clear. One thing that's become more clear is, well, so we know that there has to be some additional amount of LINAC, and we also know that there needs to be a ring of some sort or multiple rings. Okay. And that ring could be an RCS, it could be a compressor ring. And do we need a compressor ring at 800 MeV? That's one of the proposals out there. Do we need it at 2 GV? Do we need it at 8 GV? But
Do
there's
we want
going
to
to be a
keep the
ring of some
recycler?
sort.
Do we want to keep the recycler? That's another question that
Right,
do we
right,
want
but-
to keep them on campus? I mean, there's
Well,
overwhelming.
You made a very strong argument yesterday for keeping the recycler. So that, and because of not putting in a 2-year stop.
Well, okay, I also wanted to support, I know it's not the same, but I agree with Bob that 100 kilowatt target may not be that much different in cost and infrastructure than the megawatt target. I mean, look at all spallation neutron sources. They don't build 10 100 kilowatt targets because it makes absolutely zero. It makes no sense to do it this way.
Yeah.
From the service infrastructure and cost point of view, they just built one giant target. I mean,
Right.
it's just if you think about. Okay, so anyway, I'm supporting Bob on this.
But Sergey, if in the case of the neutron sources, many of the experiments depend critically on the brightness of the neutron source, and certainly you don't get that brightness from 10 targets. So I'd say it's more than just cost, and I agree with you about the cost and infrastructure, but you really need it for a physics reason.
Okay, yes, I got your point, Bill. Thank you. Yes, but certainly my argument is correct about the cost and the infrastructure because
Absolutely, agree with you.
just, if you build 10 100 kilowatt targets, it's going to be astronomical in terms of. Okay, thanks.
I wanted to come back to some of Scott's points. I think listing and being clear. So one of the challenges, as I understand it, in this area, in this field, is that there's a few facilities that are heavily oversubscribed, and then there's not a lot more. So as PIP2 comes on, and if you guys define how you can use PIP2 and modify the upgrade to take better advantage of it, that's great. But I think you should also list the other things where you can operate parasitically. And that comes maybe not for free, but it comes very inexpensively compared to upgrading PIP2, which will have a very significant impact on the HEP budget.
And just to circle back on Bob's comment, I mean, there were several, at least LOIs, that were proposing fully parasitic experiments at various colliders and neutrinos. Maybe the physics case wasn't there, but we did not really read those. So they some people think they can do things parasitically. There's weird parasitic experiments at there's Millikan, there's these weird little parasitic experiments at the LHC.
Well, Bill mentioned using the European XFEL beam or using the LCLS2
Yeah.
beam or using the LCLS1 beam. Those are parasitic experiments. Those machines are
Yeah.
going to operate funded by BES. And if we can tap into that, that would be a nice flow of
Yeah, that's
of
actually
resources
including those facilities is,
Right.
is really
back
is
from BES, which HEP has contributed to very heavily in the
yeah,
past.
no, that's a
Yeah.
good that's a good point. But yeah, I think I'm very familiar with this because with another hat I run like a cyclotron that provides radiation effects, and you find that people use whatever facilities they know about. Like people don't even know other places exist. Like you can do all kinds of things at medical cyclotrons. I didn't even know that. They all let you work there on the weekend, but more questions? I through a scheduling error on my part, we left Richard's EDM talk out. And so I would like to cede, was there one more question? Or? Oh, no. I would like to cede the last part of this to his talk on EDMs, if that's okay. Again, if that seems weird, it's entirely my fault. But I think this was really fruitful, and I will go back and listen to the recording for what was said. We'll update the report. Again, I encourage people to read the report, send any substantive comments. We'll get to typos later, but send substantive comments and we will try to accommodate them or at least address them. Yeah.
Eric, you probably know how this rare processes frontier, operates. So will they come up with some priorities of any kind, something that, like experiments they would like to see first or whatever? Because showing this enormous list of opportunities without understanding what is going to happen, what is not going to happen, at least it's counterproductive for us. We should have a little bit better guidance. And I wonder how this rare process frontier what will they come up with?
I'm the wrong one to ask.
Okay.
Yeah.
So you're
I'm
not coupled to
very
them?
close to the charged lepton flavor violation community. That's my
That's your
vision. So
I see.
I would talk to Bernstein, who's also a very lepton flavor violation center. So I would definitely talk to that group though.
Okay, thanks.
Okay, thanks. And apologies for all the confusion. All right. Oh, I have the
Can you hear me now? Okay, I want to talk about detecting time reversal invariance by measuring the difference between the proton and the helium-3 electric dipole moment. Why doesn't it advance? Oh, I was pushing the wrong way. Okay, this is the subject, but it's roughly speaking one subject per slide, so I don't need to read this. Okay. The ring to measure the electric dipole moment of, say, the proton or the helium-3 is a ring of a radius 11 meters with superimposed field inwards and magnetic field upwards. Now, the idea is to have frozen spins, meaning the spin tune is 0, meaning that the spin is aligned. If it starts aligned with the momentum, it stays aligned. Now, the reason the spin precesses is because of the magnetic dipole moment. Now, if there were an electric dipole moment, it would cause precession out of the plane. So the signature for an electric dipole moment is precession out of the plane. Anyway, so we have a 49.7, many decimal places, MeV protons circulating clockwise. At the same time, we have 24.7 MeV protons. They're not globally frozen, they're pseudo-frozen, meaning the spin tune is -2, meaning instead of staying aligned, the dipole moment actually flips around twice. Now, the reason this works is because for big rings going this way, the bending is constructive, whereas for a beam going the counterclockwise, the bending is destructive. So up here we have electric and magnetic bending adding to a big vector, and down here we have electric and magnetic adding to a little vector. And that's why this is a 24/7 MeV proton, and this is a 49.7. Now, the EDM develops in the clockwise, but not in the counterclockwise because of this. The spin tune has to be 0 in order for an EDM signal to accumulate. Anyway, to repeat what I said, the EDM signature is out of plane precession of the magnetic dipole moment. Whoops, I went the wrong way. Okay, now this is a two-phase project. The first phase is in Jülich, Germany. The first I keep going the wrong way. The first phase is in Jülich, Germany. They have a cyclotron, 25 megahertz, 45 MeV, 100% polarized protons, a very low current, microamp. They have a stripper injection. Cozy at the moment is a racetrack, but if you get rid of the long straights, you move the arc over here to make it more or less circular, then the same stripper injection works, and you have to inject like 10,000 turns, 10,000 of these 25 megahertz bunches. It debunches, you have to rebunch the beams, and so you have two bunches, which this is a transfer line that needs to be built, and then it transfers two bunches, one going clockwise, one going counterclockwise, and then you actually can repeat the process. So in the end, you end up with 4 bunches in this ring of arbitrary polarization, 100% polarized. I already said this. Okay, now the ring, which is called PTR, which is because it's a prototype EDM facility, but the point is you're going to use it to actually measure the electric dipole moment. So it starts out as a prototype, but it's actually the experiment. Okay, now the experiment looks like this. I should have showed in more detail the previous transparency, but this is like 1/4 of the ring. There's a more or less cosine theta. In detail, it's a lot more. It's not a cosine theta, and inside that there's the electrodes, and inside that there's the beam. Anyway, so this is just repeating what I said before. We've got 49.7 magic, spin tune 0 going one way, 24.7 pseudo frozen, spin tune -2 that do not provide a FDM signal going the other way. And the important parameters are the circumference is 102 meters. The radius, I already said, it's 11 meters. And the currents are approaching 10 to the 11th protons stored. Okay, the essence of the optics of this ring is sketched in this picture. It's distortion-free, quadrupole-free, doubly magic, two-way toroidal optics. And each of those things means something. So it's electric magnetic superimposed. This makes it a magnetic dipole moment comparator. That is, say, you can compare the magnetic moments of two different particle types. It's astigmatically corrected, thick lens, no quadrupole, toroidal optics. It's nearly identical forward and backward optics. For the vertical, it's exact. This is exactly valid beta functions for both clockwise and counterclockwise. I'll get in a moment to the proton helium-3 case where it's even better. But anyway, the horizontal beta functions, they have the same shape, but the amplitude is a little bit different. I'll show you in better detail. Okay, so you have nearly identical forward and backwards, vertical exact, horizontal perturbative. You run on the sum resonances. The horizontal tune is 1.7074. The vertical tune is 0.7073, which is the same. And as a result, the beams are round, or the equal emittances. So running on the sum resonance, all spin decoherence modes are canceled. In particular, because you're running on the sum resonances, any betatron contribution to spin decoherence is canceled. Because you're running in the toroidal geometry, the nonlinear resonances are essentially canceled. And because of the synchrotron oscillations, the energy decoherence is also canceled. Okay, now the second phase, the problem is in Jülich, there's no polarized helium-3. I was happy to hear Scott Berg, who's at Brookhaven, because the second phase has to occur at a place that has a highly polarized both protons and helium-3. Now, in this case, it's the same argument. Well, this is a sketch of the Brookhaven site. This is the AGS, which by now is an injector for the presently at RIC and soon EIC. Anyway, there's a proposed facility called the Center for Linac Isotope Production, which will produce 100% highly intense helium-3. So this is a picture, which I didn't really explain before, but this is the lattice with the toroidal. It's basically just 4 spectrometers, each feeding each other. Anyway, and here's a picture of this proposal. This is one of the buildings in the proposal, and this just to show the scale. This ring, which is something like 38 meters across, essentially almost fits in this building. let's see, I'll just read out the bottom. It says the dominant systematic, I already said this, but the point of the subsequent discussion is that we're going to measure the difference between the proton and the helium-3. And the reason this difference is so important is that the dominant systematic error in the EDM measurement is canceled in this difference. So presumably the helium-3 EDM, if it's either 0 or it's probably bigger than the proton. Now it could by chance be the same as a proton, in which case that would be disappointing. But basically, if this difference is anything other than 0, that's evidence for time reversal violation. Okay, so the cancellation of systematic errors. Well, this just reminds you that the signature for EDM is out of plane magnetic dipole moment precession. The dominant systematic error is radiomagnetic field error acting on the magnetic dipole moment mimics the electric field acting on the EDM. In other words, it's an indistinguishable background. So, but in the combination, let's call it delta, this systematic error cancels. So non-zero delta implies beyond standard model physics. So gyroscopic phase locked clockwise, counterclockwise reversal. Reversing, in order to reduce the systematic errors, one wants to run protons clockwise, helium anti-clockwise, and vice versa. And this, it requires reversing the magnetic field. So setting, reversing, and resetting the magnetic field with frequency domain accuracy relies only on the MDMs acting as magnetosensing gyroscopes. This is applied in determining the masses of resonances discovered in E plus E minus rings. So it's a well-known phenomenon. This avoids the need for unachievably precise magnetic field measurement while allowing systematic error reduction averaging over clockwise, counterclockwise reversal. Counting statistics. I define a nominal week, which is 7 days divided by pi. Sure, okay, I'm almost finished. I'm almost finished, okay. Anyway, so it's like 2 days of running time. If you run for runs of length 2 days, the statistical error is 10 to the minus 29th. And so we can forget it. It's going to be, that's going to be a limit. So the important thing is a systematic error. And I've described various cases. It's just a single ring, the systematic error will be around 10 to the minus 27 electron centimeters, which is more or less the current limit on the neutron EDM. Here's concurrent running, and since time is short, the end result is with concurrent running doubly magic, the systematic error is 10 to the minus 29 electron centimeters, and taking account of this differencing here, the error will be less than 10 to the minus 29th. Thanks for your attention.
I think we do have to move on to the next session, but thank you very much. Again, I apologize for scheduling.
Tried to round people up because some like Craig Burkhardt, I think, wanted to come, and without, oh, okay. I just didn't see. Okay. All right, this is AF1 session. I'm gonna go over education, outreach, and diversity in accelerator science and engineering. In AF1, we covered topics within accelerators, education, outreach, and diversity. I got kind of tagged with shepherding through that part. We also covered research centers and facilities. Zhurong Huang was the main convener for that, and the physics limits of ultimate beams with Mei Bai. And following me, Mei is going to present from Zhurong and herself on topics 2 and 3. And then we also combined with the computational frontier on computational tools and machine learning for accelerator science and engineering. And Jean-Luc Vey, who's here, will cover that after me. Just in a very abbreviated sense, Mei will go over a little bit more details in her set to follow. But we have a white paper that is covering education, outreach, and diversity issues in accelerator science and engineering, and I put the link in the slides. Okay, first, accelerators for education. The university, oh, what happened? Geez. Well, something went wrong on the slides. Something got. Well, maybe I can do it off the cuff. The universities have very limited faculty representation due to university. Well, there's limited university-based facilities, projects, and grants. There's relatively poor representation in department colloquia series, and all of this comes together to hinder recruiting and drawing people into the field. Recently, the Department of Energy started accelerator science and engineering traineeships. 4 traineeships were funded to start students launching in our field. The present traineeships were started with MSU in 2017. And then 2 years after, Stony Brook and Cornell collaboration and Illinois Institute of Technology and Northern Illinois University were added in. And then finally, last fiscal year, Old Dominion University together with Hampton University and Norfolk University were added in. So there are now 4 of these. And at steady state, these should be launching 15 through 25 graduate students per year, most of them with master's focus, some with PhDs. And the traineeships are set up to emphasize 4 need areas in large accelerators facilities: physics and engineering of large accelerator systems, RF power engineering, SRF technology, and large cryogenic systems. Now, the other thing we have within accelerator science is adding in here the Daniel Winklener, Bill Barletta, and Richie Patterson provided a slide here with a summary of accelerator projects and facilities at universities. And this provides kind of a good example of what a bit of funding can do at the university level. For example, CBB, the Center for Bright Beams, is NSF funded, and they've leveraged this funding to go out to university partners at various institutions beyond Cornell, starting out students and bringing in people into the field. I can tell you, for example, also in ASAT at MSU, when I first came to MSU, we only had 3 students working in accelerator science and engineering. Under the traineeship, we now are up to 26, and we're starting to graduate significant numbers. And so this is good for the field, bringing in talent and things, but there has to be spending in the university. So there has to be kind of projects to bring them in and collaborations with that. Now, unfortunately, I'm missing a slide. I'll put it in the set. But going off the cuff, we basically are set up for because we don't have much university representation since '85 in the U.S. Particle Accelerator School. We've convened intensive sessions twice a year, serving, I think, about 200 to 300-ish students per year, and about 40 to 70 faculty per year that benefit teaching these courses and drawing in talent and things. And we're set up to do that because of the lack of representation. And we also teach the classes very broadly for the full accelerator field, bringing people in, and then they go off and they can work in other areas, not necessarily HEP, but they're basically primed and ready to work on projects. So we don't teach courses like SRF crab cavities for HEP. We teach SRF technology, and then they can go back and forth. And this has served the field very well. And with more and more jobs opening up in other areas and things, it's worked quite well drawing people in. Okay, now recommendations for how we can improve the situation. For USPAS, we would like to see one additional FTE of effort in that, to run a national recruiting class to draw in talent that would be truly at the undergraduate level. And I'll go through that in a little bit more detail shortly under outreach. But we also would like to use those person with an IT bent to conduct community statistics to gather up what the job market is, what the needs are. And this has to be done systematically for many years. We're in the right position to do this. And also IT enhancements for our courses, they becoming increasingly more technical, cloud computing, everything like that. We're recording things, augmenting. We need a little bit more effort to do this well and run as a benefit for the community. Also, we're in an exceptional situation where we have a woman working in our staff who's a high-level executive and started from high school in basically 30 years and has been the heart and soul of the school and the community. We need to get someone else working with her quickly and learning from her before things get approaching retirement age, or we end up in some problem, or we are going to run into trouble later. In universities, we need more funding for university-based programs and facilities, more research grants, and we need to involve professors in DOE lab projects. In the DOE traineeships, we need clear expectations to the national labs from the DOE that they want these students supported, and maybe even a mechanism to lubricate the funding for these placements. With the severe cap restrictions involved in the traineeships of 2 years and 110K of funding need to be relaxed. This is basically between this and the timeline, some of the programs like University of Maryland were told they could not apply. Stanford analyzed the situation and said it was no way to make it work. And if this is broadened up, it will be good. People are also forgetting on internationals, we are barring them from going in the traineeships. I know this is difficult to deal with, but look around the room. Most of our talent is from all over the world. This is a strength. We need to bring in these people, and I don't know how you can do it and convince government, but somehow get the message. Maybe they sign some agreement to start out in the USA or something, and things will take its course. But and also have some expectation that these things can continue beyond the 5-year grants, because that's not that much time for a PhD. And a lot of programs like FRIB, without Thomas Glossmacher's support and overhead, we would have been told not to do that at MSU. And we wouldn't have these 26 students for the field. Now, in outreach, our field is very healthy in accelerators in spite of the trouble with HEP projects. That's because in nuclear physics, there are also large projects. There are a plethora of light sources, spallation neutron sources for material science, biology, and medicine. We have medical applications. We have industrial applications, NNSA, and as time goes on, more and more. We basically have a very flexible toolkit for our field that can be applied to all the different areas, and HEP can draw back with these when we get projects. But most of our recent grads, they can find work in national labs, academia, industry, and medicine. They don't have to be Superman or Superwoman, and they can get out into good fields and be difference makers. In spite of this good situation, we're finding it very difficult to recruit people from accelerators into accelerators. We say we're a broad field, interesting physics, high impact, but they come in with listening with jobs. But if they were thinking of being condensed matter, high energy physics, MP, they don't sign up for us. So we need to do something to address this in our profile. We need also the faculty representation to do this. We need to maintain DPB representation, signing up people, everything like that. Now, in the universities, we also see there's a lot more stress with the younger generations, exams, qualifiers, research stress, the discourse tone, all of that. And keep in mind, graduate studies are intrinsically difficult. We can't make that easy, but we have to do better kind of serving the change in the situation. We also need to attract the best talent we can, retain them long-term for the benefit of the field. And we want to draw in the full community with balance and representation of gender and ethnic groups and everything, and put them in the best positions. Now, this is how we do all this is a difficult question, and there are many different perspectives. But I think a lot of it hinges on recruiting and increasing our pool. Now, some suggestions on recommendation how to do that. We need to run a national undergraduate level talent recruitment course once a year, not with USPAS rigor at our graduate level or fundamentals, but something light and not HEP specific, but just look at this broad field, what you can do. Bring in a dynamic lecturer. It probably rules out me teaching my space charge course or graduate accelerator physics, but someone fun without so much nuts and bolts with it, and not run a little bit differently. Hold it at accelerator centers and maybe rotate around the country, or have it at Fermilab at a large facility. We could organize it with USPAS, but we need more person power with that. On top of the pandemic, if I ask our office to do this, they're going to rightfully kill me at this point. And so we need to bring someone else in for these other reasons and run this. We could also enhance recruiting for this, try to draw in women, underrepresented minorities, and that's the real issue, getting people in, and we're trying to solve it too late. Fully fund this where it would be a paid tour where they have all expenses, including travel, coming in. And I'm pretty sure we could advertise this and get it to work. We also need lab programs to support colloquia in the universities to broaden our profile and reward outreach in the labs, have expectations of that in performance appraisals and reward them for it. Okay, in equity, inclusion, and diversity, equity, inclusion in accelerators. In the US Particle Accelerator School, we recruit women and underrepresented minority instructors with the theory that if we do this and put people in positions of lecturing and things, it sets an example and helps draw in. I think it's been slowly working. We also instituted a URM scholarship we named after the Wilson Award winner, Sakazi Matingwa. It's been helpful in getting increases. I don't know, it's too early to tell with 2 sessions, but we've gone from 1, say, African-American ancestry person to about 3 or 4 per session now, which seems tangibly better. And also Hispanic, we're up to around 15% in total with this. And so that's good, but we need to not say it's good enough and continue on and try to double down and do better. In fact, if you look at the data we have in USPAS over 34 years with the percentage of women in it, we've certainly gone up. But if you would have told me 34 years ago when I was a student that it would only go up by this much with the emphasis, I would be have been a little bit surprised. So what can we do to make this turn up a little better? And here are more recent percentages of women fraction, and you see underneath the percentages of women instructors that we're trying to boost. And I unfortunately, I didn't have the data in the plots for the last 2 sessions, but they're bumped up a little bit higher. And I pointed out, here's a table of women students at one of our sessions that would have been unthinkable years ago to see 1, 2, 3, 4 women right around a table associated with one class. And so I think this is a good trend on sign of things to come. But now, what can we do better in diversity, equity, and inclusion? We can supplement the yearly undergrad recruitment and training class to try to boost outreach with this. We can go over to HBCUs and try to reach out through channels for recruiting of women with the appropriate peers giving talks and things. Sakazi Matingwa has already agreed to do this post-pandemic for us, and I'm hopeful that that will work. Probably this needs to be funded by field work proposal rather than a grant, because again, this needs to be done coherently for a long time. We need to also initiate programs to address the quality of life issues in the lab. So a lot of people came up, and this is something I never would have put down myself, but they say, you know, we have young kids and the technical lifestyle is very difficult. And this is not just women saying this, young men and all, it's not really a gender issue. But we have some difficulty with that. And with the increased sensitivity, the way discourse is happening, we need to do a little bit better in training people in expectations and things of what should happen and how to conduct. And I honestly believe most people don't have ill intentions with stuff like this. And I've seen it in USPAS. We have an old school model. We ask a really lot from the students, but the instructors are sitting in there working with them and helping them. And we don't trigger much complaints. But if the instructor basically ignores them, goes off in their room preparing the lecture, and the students find they're looked down upon, believe me, we trigger complaints with the stress then. And so I think there's a lesson from that in the community on how to go forth with this. Now, I put, May will have this at the bottom before we go in the discussions, but I put a summary here of the ask for the, and these are covered in the talk. So, okay, next.
Thank you. Right. All right, so I will try to be as short as possible because the goal is at the end, we leave enough time for the community. This is on, right? No, I want to change the slides. You don't hear me.
I can hear you, May.
Oh, this one. Can you hear me now?
Yes.
Awesome. Okay, this doesn't work. Oh, let's fix this one. Okay, so I will try to be as short as possible because the goal is the end to hear from you. A lot of the issues already brought up. Does this work? Ah, perfect. So as Steve already gave you how AF1, the scope of AF1. So here's the point of the pointer. So this is what we have received at the beginning of the Slow Mass 2021 of the letter of intent as a total of 61, and they touch a broad, quite a broad range of the topics. And then based on those, we within ourselves, we organized in 4 topics, as Steve already alluded to. In the end, we also ganged up with G and Gianluca, who will give you the summary from their side right after me. So we carried our activities into a regular conversation among ourselves. We organized
a series of workshops on the physics limits of ultimate beams is to identify, are we there yet? Are everybody talking about quantum limit? Are we there yet? So for colliders, this is really more or less for collider, but I want to use this opportunity to emphasize these ultimate beams are not only for colliders. There are all other areas also pursuing similar beams. So I think in the audience, I hope whoever wants to chime in later, please do so, let us know. You can also share with us your interests. And these are the topics, just a quick hash of what was covered. And this is all captured in the Indico page. In summary, out of the physics limits of ultimate beams, Tao Han and Lian Tao, and also Michael, many of the particle physicists from theory side, from the experimental side, express their wish, what their holy grail is. And this message has been very unanimous and coherent. They want multi-TeV, that be the lepton and hadron. That is the holy grail, not only the multi-TeV, but also with the luminosity. That's what they're going after. So, and that's the area. Mintigua actually has a very good term for it called the golden desert. You will hear from him later on. And the conventional RF accelerator that we have been working with has not yet. We have, you and I, many of us here have had our own shares of pushing that limit in the control room, in simulation, but we're not there yet at the quantum limit. Frank actually, and also Vladimir had quite some papers out there to show why it's not yet. But definitely we have been facing a lot of challenges. As I said, needs a substantial R&Ds. And the ongoing advanced concept using plasma wake field, whether you drive it with a laser or you drive with beam, or other disruptive acceleration technologies. There are discussions about using the nanotubes. This could have potential to reach the ultimate beams at the quantum limit. The field is young. The field is making a lot of progress, and it's not yet ready to tell whether this is going to be there or not, but it definitely has the potential to reach the ultimate beams. So as I said, the whole series is showing that we need to test the facilities. A lot of these ideas needs to be tested. All the accelerator facilities we know are user facilities. Their primarily goal is to go to their scientific program. So it is not really in a position ultimately for pursuing some of these ideas. We do have some facilities. I think John Power, is he here? Right, he can chime in later on in the discussion. And you already heard from Steve, we need people. At the end of the day, we can have hardwares, but the end of the day, we need people to make these hardwares and softwares to give what we want. So we can talk more later on. We also had our community meeting in November. Was it November? Well, no, end of November in SLAC to discuss how to approach the white papers. We received a number of white papers, as you can see here. It's also available on the SLOMAS wiki page. As based on all these inputs, and thanks a lot for the whole community engagement, we put forward a summary of our finding. We feel that the accelerator and the beam physics is a cross-cutting through all the endeavors, the scientific endeavors. And there's a collider physics. There is also ultimate light source, let it be storage ring, let it be Linac driven. All these are, what's underneath is the accelerator and the beam physics. The HEP frontiers have been pushing the accelerator performance towards the ultimate beams. And so are some of the photon scientists, right? What they need is also pushing towards the ultimate beams. I think my co-convener, Jerome, probably could also say a few words about it afterwards. And I think there was a series of workshop initiated by Sergey and others, identified the 4 grand challenges in the beam intensity, in the beam quality, in the beam control. What was the 4th? And the beam modeling. So these are the 4 challenges has been identified. And R&D at the university has a tremendous of scientific education value. You already heard from Steve. More you will hear from the audience later to make accelerated R&D visible to undergraduate students and the graduate students, creates a pipeline. So we cannot keep on talking about recruiting so and so, how to have the inclusive. If we don't have an inclusive pipeline, good luck, folks. So one thing is the funding. At the end of the day, money talks, right? Without money, we're not happy because money talks. The funding in GARD has not been, sorry, this is not gonna, has been declined. You already had a quick look of the slide, next slide. And the NSF has canceled its support to the accelerator science program. So funding is the key, and to draw people in and together with interesting topics. So I stole these 2 slides this is from Harrod Kahn's presentation. You can see remarkably over 10 years of time in the total number of sheer dollars of the core research, there's a little bit dip, but more or less constant. But we all know there is a inflation. So if you normalize this, some point, this is factually is declining. So you can extrapolate using your eyeballs, right, to see where it's going to meet 0. That goes with the pipeline. And it's a leaking or shrinking pipeline, so to say. And this is I stole from Vladimir's yesterday's slides. Took a phone. Phone is useful to take data these days. I learned that. This is even more gloomy because this is even without me doing the normalization with the inflation, you're already declining. So the slope will be even more accelerate towards 0. So this is really an issue. So we put forward only 3 recommendations. I think the recommendations needs to be actionable. We believe these are actionable, but we need your help as a community to make sure this is actionable, right? So we need to establish a decadal roadmap. We understand that there's the pocket of money. The pocket is limited. We understand we're not making money. So we need to prioritize as a community, what is the roadmap towards our goal, yeah? And we also, we also recommend to reestablish the collider specific topics. We noticed that these collider related topics have not yet been, we call it slowly drifting away from the continent of United States to the continent of Eurasia. So I think at the latest APS meeting, I asked, do we still have a chance to have our collider? We know there's EIC, but what's going to be after? Or do we see ourselves as technology or science providers for Eurasia? So that's okay. I mean, that has to be consistent. Strengthen and expand the capabilities of the US accelerator beam test facilities to maintain our competitiveness. If this is also aligned with the funding agency's goal, then we need to make sure we have not only the people, but also the tools to make sure they stay with us and to be successful. And that's about, oh, this is Steve already shared with you from his side, from the education side, from the outreach side, from diversity side. So the message is coherent here to say, if we don't have a robust program, charming program, attractive program, and with the needed resources to be to pair it up with, and the pipeline will continue shrinking, we're leaking, we'll never get to that pipeline we want to be. All right, thank you very much. And we have Gianluca and G. We have to switch the side. Yes, we go through the talks first, and thank you. So Vladimir, still be patient, patient. Thank you. Yeah, exactly.
This will be the first one. Second. So if you click, hold on. Perfect. Okay. Good morning, everyone. So I'll try to be as short as possible. Okay, so I report on particle accelerator modeling on behalf of the beam and accelerator modeling interest group, and I'll tell more about that. As you know, all computing was part of Comp F with a number of subgroups, and this is part of the Comp F2 reporting. Let's see. Okay. So who we are, beam accelerator modeling interest group, so that a group that was formed to be as inclusive as possible. In Comp F2, there's a homepage. So what we did is we had multi-year effort with regular bi-weekly meetings that involved over 80 people in our mailing list, with at least a third regularly active, that generated about 26 LOIs to SNOMAS on accelerator modeling. Those LOIs, the material was largely reported in 2 community papers in an ICFA Beam Dynamic newsletter last year. And we decided collectively to distill all the inputs and topics into only 1 community white papers for SNOMAS. And the content was then distilled by G for the Comp F2 and the Comp F reports. So you see here the front page of the white paper. So you see that there's a number of co-authors from a relatively large number of institutions. And so a few key observations that in the introduction of the paper is that computer modeling is essential to beam and accelerator physics research, as well as to the design, commissioning, and operation of particle accelerators. It's a large and complex endeavor with expanding range of intertwined physics topics.
Hey, Robert.
Sorry.
Not
it's
too
rapidly
bad.
changing and disruptive
Sitting and
computing
listening
hardware
to
and
an
software
extended
environment.
meeting, but
CPUs, GPUs over
I failed again yesterday.
quantum
Just
and AI/ML. So it's getting really more and more complex.
bravo
Interesting
for you.
point is that contrary
Amazing.
to machines and accelerator complexes, development of beam and accelerator physics
bad for you.
often largely coordinated. And that's an important point. So we got a lot of inputs that we've arranged under a number of topics. So modeling needs of many topics: RF-based acceleration, plasma-based, structure-based, and so on, including also structured plasma, magnets, many topics. Then looking at the next frontier toward ultra-precise, ultra-fast virtual twins of particle accelerators, a number of subtopics. Then cutting-edge and emerging computing opportunities. That includes better algorithms, but also AI, ML, differentiable simulations, quantum computing, computational needs in hardware, software, scalability, IOs, in situ analysis, then sustainability, reliability, user support, and training. So that, of course, connects to some of the talks that you've just heard, with number of subtopics here. And then recognizing that we can do better by working more together than looking at integration, loosely coupled, tightly coupled, data repository centers and consortia collaboration with industry. So all of this, okay, maybe just quickly, there were in the white paper that was submitted, recommendations that were drawn for each of the subtopic here. So you can go and look it up. But realistically, this cannot go into the final report. So we then distilled higher level recommendation, which I will go through here, which are by nature very cross-cutting. Okay, so first one is to develop a comprehensive portfolio of particle accelerator and beam physics, something I don't know, so in support of achieving accelerator and beam physics thrust grand challenges of intensity, quality, control, and prediction. So this is mapping exactly to the topics that I mentioned right before. And comprehensive means that addressing all the RF, technology, accelerators, plasma accelerators, magnets, and so on. Second recommendation is to develop software infrastructure to enable end-to-end virtual accelerator modeling and corresponding virtual twins of particle accelerators. And that addresses also one specific grand challenge that has to do with prediction. Third recommendation is to develop advanced algorithms and methods, including AI, ML modalities, and quantum computing technologies. Recommendation 4 is to develop efficient and scalable software frameworks and associated tools to effectively leverage the next generation of high performance and high throughput computing hardware. So that includes leveraging GPUs and exascale supercomputers. Only a small fraction of particle accelerator codes actually leverage those. So very important topic. Fifth recommendation is to develop sustainable and reliable code maintenance practices, community benchmarking capabilities, and training opportunities to foster the cooperative application of accelerator software. And final one is foster an open community that spans academia, national labs and industry to first develop software ecosystems. So not just a large collection of completely independent and not interoperable software, libraries, frameworks, and standards. Standards very important. It's only one word here, but if already we can standardize all the data, and that's key actually for AI/ML. It's a big topic in the subsection of AI/ML in CompF to have standardized data, because otherwise it's very difficult to use AI/ML efficiently if you have data that is just readable in many different or writable in many different ways. Second, curate data repositories. Of course, that's connected to standards too. And finally, establish dedicated centers and distributed consortia with open governance models. So again, trying to centralize a little bit and better coordinate all the development maintenance of software. And this is it. So we can discuss this. Let's see. I thought I had. Thank you, Stein, but that's okay. We can discuss it further into the next portion. But I think that's John. You have a talk first. I mean, next. So there should be, if you click again. Oh, it's coming. If you click again, you can download the second talk, and that's John. We'll give it. Yeah, this one.
Yeah, these are mine. Hello. Okay, good. So I'll give a quick talk on US beam test facilities, and I tried to upload something, but probably it didn't get there in time. Okay, so this is about the US beam test facilities, and it's on behalf of some co-authors. So there's a white paper here. What I didn't mention is this work on beam test facilities ties very tightly with the accelerator and beam physics roadmap, which is being worked on. But this one just focuses on beam test facilities, and you can see the list of author affiliations here are a mixture of laboratories and universities. Okay, so well, of course, the main purpose of the beam test facilities is demonstrating the viability of any emerging accelerator science ultimately relies on experimental validation. So you can, like you heard from John Luke, we do modeling, we do theory, but at some point we need to experimentally validate the techniques. So we provide, the test facilities provide the experimental test beds to carry out basic research and advanced accelerators. And as May Bai pointed out, that some of this can be done at user facilities, but in reality, the users are king there, and there's very limited time, and you need these test facilities to have the flexibility really when you're exploring new ideas and not just like machine upgrades. And the second part of the mission is in all of our fields in HEP, of course, it's to develop these intensity frontier facilities and energy frontier facilities, but also societal applications. And the last thing which you heard about with Steve talking was, oh, is this a new one? Okay. Or no? Oh. Oh, no, it's not advancing. Okay, no, this is still the same one. Okay. Oh, and then the last thing is what you heard about Steve's talk is this is an excellent place to do traineeship. And it really is one of the places, the beam test facilities, like at what we do at AWA, is one of the places that students can actually get their hands on the accelerator, which is a very different situation for a user facility. So again, the ultimate goal here, if I summarize, is to enable that next generation of science facilities, but also to train the scientists who are going to have the skills to design and build those next facilities when we're gone. So what we put together here is a mixture of test facilities from both universities and national laboratories. And the way we did this was just to keep things manageable, which maybe wasn't the right way to do it. So I'll talk about that in a second. And maybe we can talk about this in the discussion. Is down at the bottom. I don't know if you can see, but we kind of drew the line at test facilities with 100 MeV order of 100 MeV drive beams and order of 10 petawatt lasers or gigawatt RF power sources. So this means it's a smaller number, so it made it easier to write the white paper, but this leaves out many important smaller test facilities like Pegasus at UCLA. And I think there was some discussion last night among university people about, and I think we saw that list on the first slide that Steve showed of the many different test facilities that are at the universities. So one of the things we could talk about is we right now have a collaboration that's been going pretty well for the last couple of years. We call the Beam Test Facilities Council, where we're meeting, where the GUARD test facility, the national laboratories are meeting, but maybe we expand this so there's more coordination and learning from each other among universities and national laboratories. And even at this point, it's a new effort. It's, I've been in the field a long time, and this is the first time we've actually started working together. It's a big first step, and it's still a learning curve, but now is probably about the right time to start adding on other programs as well. So here you can just see, I won't read through the names, but you can see this mixture of university and national laboratory programs. And here in the white paper, you can see a little bit about each of the different facilities. We all provided a layout for the national labs and the universities. If I go to the next slide, what we tried to do, and this is only the work here so far of the GUARD program, but we tried to see, first of all, identify what are the research thrusts and how much overlap is there between them. So there's, working on the laser wake field that helped. I won't go through this whole table, but just as an example, working on laser wake field acceleration, you have ATF and Bella, and then you can go through here and see what each different research thrust is. And over here, then you have to have some set of capabilities. And first is just kind of like the botanist, just kind of mapping what we have, what capabilities do the national laboratories have in terms of providing. Here's a case of what's the energy of the beam. So facet here is the only one with the, well, that's planned. P means planned. So, but a 10 GeV drive beam for the electrons, that's facet. And again, just exploring what those capabilities are. And I think it gives us a better, it's more open, more transparent to see what people are doing around the country. Okay, so I won't go too much longer, but just to say here, one of the things we emphasize is there's been a lot of progress made at the beam test facilities, although the test facility, it's not the progress of the test facility per se, they serve the GARD roadmaps, right? So there's a roadmap for AEC. This is a bit biased towards AEC. And so here are my examples. There's been a lot of progress made at AEC in that AEC roadmap, and that's been done at these GARD test facilities. And now as ABP is coming online, ABP also has roles on beam shaping and these. So I think you have to think of like a few of these things like ABP and GARD are really more the general purpose to serve the other parts of the more focused parts of the roadmap. I think that slide. Thanks. And I won't go through this. I thought this was an interesting list we put together. Aside from progress since the last snowmass, these are the, let's say, spin-offs that have happened in part at some of these US GARD test facilities. And you can see a lot of these first ones serve, the development of the photo injector happened at some of these GARD test facilities, which now we have XCFELs because of these. A lot of these you see here are in the light source community, but those are because these are the near-term applications. And this is the way you get to the high intensity and energy frontier in the HEP roadmap. So now comes really to the recommendation is that the US GARD test facilities will require significant investment. And I know we keep hearing the same message, and where's the money going to come from? I don't know, but we just have to explain what we see is what we need. But these upgraded test facilities are needed to keep the USD HEP program cutting edge in both the energy and intensity frontiers. And we all know what's going on in Europe and Asia right now. Examples like Eupraxia is a $400 million program. So there's large investments going on in other parts of the country. So or other parts of the world. So in order for us to stay competitive, we need to support the test facilities. And in the long run, several options are being considered for reusing infrastructure on next generation facilities. And this, so again, this example here is a little bit on the AEC side, but that investing now in the AEC side gives potential payoff for the HEP roadmap. So I'll just end here with recommendation. I didn't have time to add what Richie said, but I think, so I said, let's continue to hold these. I think this has been a great development and it's free, so we want to continue to have this Beam Test Facility Council and expand it to get more coordination among the accelerator programs. And then I think here, our main recommendation is support for these US Beam Test facilities, because these are going to enable those next set of facilities, train the future scientists, and serve the other parts of the GARD roadmap. And I think I'm the last speaker. Well, right now, if you go back to this roadmap, you only see these 9 facilities. And the idea, and we drew the line here for these meetings and for the white paper are these kind of large scale facilities, but there's many small scale university facilities. And we saw that Steve showed a table that had a long list of what's going on, Michigan State and and NIU. And, so again, increasing coordination there because these are free efforts. And Pegasus.
Yeah, I think
certainly it would be interesting to coordinate. I mean, I don't know if each university facility has really the bandwidth to participate, so you guys should take a lead. But I think it's good. There are a lot of things that are useful to know even in practice, like hardware missing or like that it could be useful to share and like to understand. And I think that at UCLA, sometimes we get calls from Slack or other places. You do this, or what do you need? And that's that would be useful to.
Yeah, that's exactly right. We've been overwhelmed with snowmass preparation, but we had meant the original intention was to alternate between these kind of big planning processes and just sharing like some low-level work on, what are you doing for your low-level RF system? And there are like excellent groups like the Bocce group at Berkeley that we've started using, but there are other facilities have to go through these same exercises, and just awareness of like, there's another program. Yeah, I think this is really where sharing that practical experience.
Yeah, so it would be good to be observer or something like that, like and just have a channel of communication open. I don't know if you should expand it all the way, but yeah.
Right, and right now this is monthly meetings, but we could do quarterly. Yeah, there's lots of ideas, but something. Yeah.
I have a quick question. Oh, sorry.
Actually, advantage should be given to people who didn't participate in your discussions and have questions from, I would say, outside. So, for example, John Bird. While John is preparing, my high-level questions to Steve Land and to you, John. So you show 9 facilities, 9 good facilities where people can get beams. At the same time, claim is that we are losing the game compared to Europe or the Eurasia. Are there numbers for Europe, for example, available? So do we really know that we are doing worse or better or about the same as Europe or China or Japan?
Yeah, it would be good. Maybe somebody else knows the numbers better, but I know the Eupraxia total investments 400 million, and again, it here depends.
560 to be precise.
Pardon?
569 million.
Yeah. Okay.
Euros.
So even, and that's good. And then in here, I mean, the NSF program, I don't know. So here the universities are basically NSF sponsored, or things like LaserNet USA.
Let me reformulate. Can we make an argument as a community that we are losing the race to either Europe or Asia? Is it statement correct or not?
Yeah, I think it is. And I think we have to, but I think in particular, you're saying, is it due to lack of investment? Right. So, I mean, the 2 examples that get brought up in AAC were the recent demonstration of lasing with the Wakefield accelerators is just some example that comes to my mind. But then I also think like financially, you have large investments coming from other part, but I think we need to put a table together. Go ahead, John.
Yeah, it would be nice to have numbers. For example, we have 9 facilities of that class and Europe has 29 facilities of that class. Then people would obviously see, oh boy, we are so much behind. How can we think about, advanced things? Question to Steve Land, sorry, no. Before I proceed, along the same lines. Recently, Bill Barlett, Andrei Seri, I forgot who else, published an article saying that we are losing race to Europe because they produce, I forgot, like 400 accelerator students a year, and we produce like 40 a year in the US. Is it about right? What's the situation between us and them? Are we better, worse, much worse?
I don't really know, but I don't think the disparity is quite as large as what was just quoted.
Yeah,
But-
Vladimir, remember that was several years ago, but the investments in new facilities in Europe is enormous, and I mean, Daisy is just they're just establishing a new accelerator-related technology school, which will include lasers and management practices and entrepreneurial practices. They see the problem much bigger. What we suffer from is that there's no officially sanctioned, in other words, paid for, survey done of that compares to the European
Bill,
survey that
one thing I had in my proposal was in the extension of USPAS effort that we control a statistical gathering of all the students and programs and things and do this coherently year by year so it's comparable, so we can do these. Because frankly, a lot of times we're talking about things without hard data and it gets a little bit awkward because some of the perceptions are a little bit off. It wouldn't be that hard to do this. And I think USPAS is the correct place to do it.
Easy to do it. It's easy to do it incorrectly. And I would really urge that this is done by a university group with the inclusion of at least some faculty members that have experience in doing longitudinal studies that have credibility with the Office of Management and Budget. And the labs just don't have that. And let's, I mean, if you compare,
I don't know the field, it's very hard to do these.
if you,
Can we actually have some more questions here?
yeah.
John, may I make a proposal for actionable item? So we plan to have this ABP roadmap something in August, September. So
September.
how about if your council, John, gets together statistics and shows solid data on how good or how bad we are compared to, for example, Europe? That will be a good argument to ask for something new, for extra support or whatever. Okay.
So first of all, nice job, John, and all the other speakers for putting together this information. It's really good input for the process here. And you made the statement, this goes towards advanced accelerators. That's a massive understatement. This is all advanced accelerators. And I just want to urge that we come together with beam test facilities that support the roadmap going forward. There's nothing mentioned on here on targets. Targets is one of the massive issues needed for advances. There's lots of other issues. If we don't address any of those issues and we're only looking at advanced acceleration, we're not doing our job. So we need to have issues that actually address real, this is all nice stuff, but we're not covering any of the ground for any of the future facilities we're proposing here.
I just to add here that, so this is beam test facilities. So it is a subset.
You need a beam for targets.
No, but I think you're right. There's no reason not to expand, but this was really meant to be. So it's not the AEC roadmap alone. It's RF development. It's ABP roadmap. There's like 7 guard
But
thrusts.
what I'm concerned is that this gets out, we don't have any coverage of what we're really trying to do in the near future. And it's looked like we're not investing in the right things. That's my concern.
We are, sorry to interrupt, I'm Frédéric Pelmoine, one of the conveners for the target. And yeah, I mean, your talk is really interesting, and I was not aware that there was such research on the beam facility, test facilities on your side. But on the targetry side, we are doing exactly the same exercise and try to figure out what are the different beam test facilities dedicated for target R&D. So we have some data, yeah. And so we should probably try to converge on our both effort to have maybe one big group if it's needed, or just keep the 2 groups separate, but have some meeting in common time to times to work on that.
Yeah, so I just want to make sure we don't just cover AAC issues. We also cover, targets is one example. There's probably several other examples of things where we may need test facilities where we want to go forward. So I just want to emphasize that we want to cover all the important things, not just the cool things.
No, yeah, no, sure. And we have a white paper dedicated on irradiation station facilities and capabilities, including all the PID for material science.
Community questions to you. So towards community, you are.
Richie, do you have a question?
Can I say there are people waiting online? Please pay attention to people waiting online.
Who's doing that?
Thank you very much.
So I just want to make sure that we are in the discussion session.
Right.
So we should have a sort of order. How do we proceed? Right. So we should.
call on people and they speak and then.
Yeah. I will be also guiding from people on the Zoom, okay?
Yeah.
Because that's, we don't really, so the folks on the Zoom, please, I see the hands up. That's very good. All right, so let's go. Rich.
So I have a comment about NSF funding, which applies to all the talks, which very much, I appreciate all of the talks that we just heard. Regarding NSF funding, they did have a program in accelerator physics that did end. Currently, there is NSF support for accelerator physics, both through their plasma program and through the Center for Bright Beams. And the Center for Bright Beams will end, but I think there is potential for further NSF funding for accelerator research, which I think we can all agree would be great because it is a very high impact, not only for the research side, but for bringing in students. So what can we do here in this room to create a future where NSF wants to invest in accelerator physics? And I think the answer is to recognize the work that's being done and to include that somehow in the planning, to to value it, to mention it. It gets very easy, I know, to talk about the GUARD program because that is the big program, but we need to acknowledge the NSF role. And I think that if we can do that consistently, for example, in making roadmaps for the field, not just specifically for GUARD, if we can do that, then that gives NSF the motivation, the desire to invest further in the long term.
Can I interject?
If I can, oh, sorry, if I can.
I've been waiting, I don't know, since the start of this meeting, because I thought that the discussion would go along the talk, so I've been waiting. So in reference to this last statement, I want to ask the person who talked, are you from NSF?
No, I'm a researcher supported by NSF.
Ah, okay, okay. Because a question I would have is, do you know whether NSF would fund educational programs?
Think I can answer questions like that. I think that they are, if you look at the advertised interest in NSF, it's to fund good science. And so if the science that they're funding is recognized and valued, then surely that helps them understand that case.
I can back up something Richie brought up, that at MSU, we getting this asset grant, which is only $700K a year, sorry, $700K and a 5-year grant that has stimulated bringing in a lot of students growing in from basically 3 or 4 to now 26. We're graduating a couple of years. It's going to go up from here. The faculty they've started to add and other grants have come in. Now, part of this is also related to the AF5 facility being on campus and everything. But when you build up these, you get more capacity and you make a center. Richie's Center for Bright Beams getting their NSF funding has branched out to other collaborators and bringing in talent for the field, and all of that's great. And I think the argument is just how to best do that and foster it to be better with the declining overall state of grants and things associated with GUARD and other conduits, the NSF grant for accelerators going away and stuff like that.
Okay.
Well, because what I wanted to talk about and bring to the table in this group is, as Steve, you may already know, because I proposed this topic for your paper, is that we have a very productive example, very productive template of how one can run a traineeship, DOE traineeship program. However, I don't know what is your definition of trainee. In our case, because I see that you have a cap that is very high, $110,000 you were showing for 2 years. So I don't know, our trainees are 2 months, 2 full months trainees, and they come over the summer. They are from Europe and they're all graduate students, both in physics and engineering.
maybe we should take this up after. I'd be happy to
Yeah.
talk with you a little about it, but the programs are laid out in the funding call, and we have certainly struggled around them. And my understanding is they're going to evolve in some of the parameters and things that they will do.
Yes,
Okay.
of course, I am available to talk, but my point is the following, that perhaps if there is, if the specifications that you're looking for your trainees are consistent with our program, this program could be duplicated for US students, US graduate students from all of the, as many interested US universities as possible, because our program is European, but we could duplicate it for US students. And somebody suggested that it should be done at the undergraduate level. I think that, yes, it has some benefits, but to achieve the results that we are achieving, it should be best at the graduate student level. So we would have students that are already intend to pursue a master's in this program from most of large number of US universities to come for a couple of months or more if this doesn't match the requirements, but in our case it's 2 months, to the DOE labs and or these other test facilities that were shown in other locations. And I think that could be of great interest also to NSF, and this could bring in more money in addition to GRD.
Emmanuel, the traineeships are all graduate level. What I was proposing is a recruiting class for undergrads, but I can follow up with you more later. I think we have a queue of questions here.
Yeah. Bill Barletta, please go ahead.
Okay, so the first thing I want to do is just make a plea, which echoes a plea that Andy Sessler and I made before the last snowmass, is that every single talk I've heard today revolves around projects. And that just feeds into the strong prejudice in the Office of High Energy Physics that the only accelerator physics worth doing is that which feeds a big project. And I could say a big project which has potentials for big overruns. And you look at this in the GUARD program, which would be in DOE, the natural funding mechanism, and we find out that from the last snowmass, the amount of money that was available in GUARD to real grants, as opposed to money which was commandeered to support, at that point, LBNF, it was $20 million a year. The money in GUARD has decreased, and now it has continued to decrease. The money in BES, which used to be $15 million a year for accelerators, was first cut to 10 million. And then Eliane Lessner was told, oh, you have to support detectors. Oh, and then the following year, oh, you have to support X-ray optics. So $15 million is going to 5. We really need a campaign that talks about the general benefits of accelerator science, that looks to the university programs, and you say, why are facilities underused? Because you don't have users that have the money to use them. And it all reflects, it goes back to the fact that the university programs are being choked. And I won't go, I could make a long list of things. I do agree that the outreach programs need to be successful. I strongly urge people to look at how successful the outreach programs have been in the UK at both the John Adams and Cockcroft Institutes. Those are university focused, they're university led. They've produced people excellent with outreach, like Susie Sheehy. Let me stop there. That's the kind of outreach specialist we need. So I'll pass on to the next person.
Daniel, please.
Yes, hi. So first of all, thanks a lot for these nice overview talks. I'm very interested in the beam test facilities, but I will follow up offline on that. I just wanted to echo some of what Stephen and May already mentioned and what Bill also just talked about, and break a lance for university programs, because I think there are 3 good reasons why university-based experimental programs are very important. And this is, of course, very condensed. So the first one is that there are a great pool of new ideas with some freedom to explore these ideas. And without funding, they will basically die in the pipe. And if we at Snowmass focus all on the big projects, big ideas, as Bill just mentioned, then I think there will be no funding for these smaller programs. And then undergraduate and graduate students, they need experiments, they need good experiments and laboratory work to complement the courses and to fully benefit from the accelerated education, in my opinion. And then thirdly, I think that exciting experiments, and this is something that Steve already said, will definitely draw in more talent and increase the interest from incoming students.
Thank you. Anyone want to say something? Tor, was the question about, question to Ralph Assmann, if he's around. Ralph, are you on Zoom? Question to you was, what's the status of Hypraxia, right, Tor? That was, yeah, what's the status of Hypraxia project? And Sergey, you next.
Hello?
Yes, please, go ahead.
Yeah, I'm around. Question to me about this Hypraxia status, I understand.
Yes.
Now, we are now essentially in the next phase of what is called a European Strategy Research Infrastructure Project. So we have been placed on the S3 roadmap here, together with the Einstein Telescope and others. And this is an important step for research infrastructure in Europe. So we are on this roadmap. This has been approved with government support last December and announced. So we are now on the S3 roadmap. And being on the S3 roadmap, we are now preparing a preparatory phase project, which is funded by European Union. This is roughly a value of 8 million, 3 million, or let's say 3.5 million coming from EU, Switzerland, and UK. So we are on the predefined implementation path for such projects. Now, if we have to still find a significant amount of funding, it was mentioned, I think yesterday in the talk of AF6, that this is $600 million class, so 569 million euros. At the moment, we are at about 140 million euros. And of course, it helps us a lot that the lasing works now. In Frascati, lasing has been successful. And you might have heard that also lasing has been successful in Dresden-Rossendorf, together with Marie-Manuelle Coupry, Victor Malka, and the French team. So this clearly helps. And I would say this is the status. I hope this answers the question. We can't guarantee that we are fully successful in the end, but so far there's a lot of excitement about in Europe to have this project built. And of course, we can't predict in the present circumstances when and where we find the rest of the funding we need to build also the second pillar. But at the moment, let's say it's okay. We have the preparatory phase. We have a doctoral network funded from the European Union. There is some additional funding in Italy, which appeared recently, also from European restructuring funds. And the next step is to define this, to go in the preparatory phase, define the second pillar of Hypraxia, the laser-driven part, and define together with the funding agencies where the funding is to build a laser-driven free electric. Okay.
Simple question. The year of the first beam, when is that?
You know, it's a distributed research infrastructure. So we have several starting dates, but in Frascati, we aim at 28, 29 for the first beam.
Thank you.
Sergey, your question. Just a quick comment regarding this discussion about traineeship. I'd like to point out that, us complaining that 110K per student is not sufficient is not really helpful. I mean, I think that it's never been in the intent of our funding agency to fully subsidize, to have like 100% cost recovery on traineeship programs. We as labs told the DOE that we have problems finding new people to work on our accelerators. They listened, they've created a traineeship program. Now it's several, 4 or something. But if there are market forces in place, and if the labs truly complain and that we can't hire, they should put their money and help the universities to train students. I mean, we can't just expect the DOE to continuously add money to this program just because we complain. I mean, I'd like to point out that there's never been, it's written right in the paper in the FOA that this is not 100% cost recovery program. We, as labs, SLAC and Fermilab, we are responsible for a portion of it because we have to help these universities to provide students with research opportunities to train. I can't see how we can go back and ask them to increase funding. I mean,
Yes.
that's all I was going to say.
Sergey, I totally agree with you, and thank you for bringing that up, because I was interrupted constantly in my intervention, and I got distracted. But I meant to say also that our students for 2 months only cost $7K. So the $7K for 2 months is a very good deal. Thank you.
Steve, I would like to add something after you talk. Steve, this is Jerome. I would like, maybe you go first, Steve.
Yeah, I was just going to add a little to what Sergey said. Some of the universities and things, they scrutinize the traineeship calls, and they basically said it was an unfunded liability because of the horizon of the students and relative. And so they basically were told they could not participate. Other places like FRIB, for example, were subsidized by overhead at via Thomas Glossmacher and nuclear physics. And that's all good in getting started. And I guess, Craig Burkhart, if you wanted to, you could comment more. You said that some of those aspects may be evolving at some point.
Thanks, Steve. Yeah, so I've been asked to work on the traineeship program. We expect to have a FOA in 23. The overall workforce development in the Office of Science has been promoting traineeships across various programs. GUARD was one of the first ones in HEP. What we're seeing is there is new thinking on the funding limits for it. I think there's a general recognition that the $55K a year really does not cover the cost of graduate students in most academic situations. We're also hearing that there are challenges connecting students to laboratory programs in a timely manner so that that transition can take place and allow them to quickly get into a research mode. Right now, it's for me, it's really a fact finding. I've been working with all of the PIs on the various traineeships, trying to understand what works, what doesn't work. So I would encourage anyone from either the academic side or the lab side that has an interest in the traineeships to grab me at some point during this workshop, and I'd be happy to talk with anyone.
Who is speaking?
This is Craig Burkhart.
Okay, because we have solved that problem, so.
Fabulous.
Yeah. I may say.
Jerome, do you still have a question?
Yes, no, I have some comments regarding both traineeship and also this DOE graduate student fellowship, which basically the second program, some people familiar with, encourage university students to go to national labs to do, to have 1 year of basically additional training and doing their research. But I think especially the DOE graduate student fellowship, I believe also traineeship, require the student has to be a US citizen or permanent residency. I think that if that restriction can be lifted, and as far as I understand, the graduate student program, this fellowship program, has not been fully utilized. It's always the number of applicants has been low. Similar problem with the traineeship, also this restriction. So my question, and maybe Craig or others in the audience can answer, is can this restriction be lifted so that any US student can apply, as long as they enroll in the US universities? If I think of myself and many people sitting in the audience there, we came to US not as a citizen. We came to study, and after we find a good research topic and good way to live, and we eventually end up staying in the US. So why both this program has to be restricted to US citizen and permanent residents only?
Okay.
Yeah,
We need to wrap up.
I brought that up in the, we were advised maybe not to bring it up because it's kind of a hopeless cause. But I think it's important to kind of give some feedback on the matter, and we should all follow up with Craig and see what the situation is. But I think now turn over to Vladimir.
There is one urgent question from.
Yeah, I just want to say that I am a part of a committee that organizes the African School of Physics. We've been trying to extend high energy physics to Africa. Currently, it's basically located in North Africa, Morocco, and Egypt, and Southern Africa, South Africa. So through the African School of Physics, we've had a lot of students, and we will be more than willing to go into partnership with the US Accelerator Physics School. I heard in your talk that you would like to explore the international component. So the African School of Physics, of which Sekazi Muntigwa is one of the international advisors, could serve as a bridge to extend the scope of the US Accelerator School to that region.
Let's talk after the session and follow up. It'd be a pleasure. Thank you.
Okay, thank you. Let's continue the session. Okay, and the last part of today's morning session on accelerators is yet another dry run of our main presentation later today. So yesterday we presented everything. So we got 5 pages of comments, and Steve, myself, and Thor tried to accommodate everything into slightly tuned up slides. And as you probably recall, so we have kind of general introduction, progress since P5, SNOMAS accelerator frontier view of high energy physics, particularly future facilities on neutrinos, rare processes, and colliders, and then accelerator messages and asks. So most of the changes happen in this area. So I think what I do, I just very briefly go through each of the slides before this final 10, and then we go through final 10. So just a reminder what's in there. So we talk about our great progress on various facilities, progress on R&D. Talk about future facilities, what's in the plan for 2030s, bottlenecks, 2 options, rare processes experiments that can be done parasitically, or new facilities can be built. Then we talk about input from Energy Frontier on colliders, and other inputs we received from 4 different entities. Talk about colliders in a little bit detail, explaining their advantages, disadvantages, particularly if concentrate, again, option 1. I don't know why it's option 1 again, will be fixed. On C-Cube and Helen, go into high energy colliders, show some of them, talk about possible site failure at Fermilab, talk about the other ideas, and bring implementation task force into the picture, explain what they said about most, I would say, discussed colliders. And then this is the slide we have added. And just to be clear, that ITF takeaway is that they have reviewed concepts to allow comparison, but they did not prioritize any of the concepts.
So they also recommended, and we support them, that R&D to reduce cost and energy consumption of future collider projects is given high priority. Basically, instead of bringing it as Accelerator Frontier, big recommendation at the very end, we discuss it kind of its outcome of ITF exercise. And ITF evaluations could be updated on a regular basis if necessary. Yes?
You might want to add that caveat that the ITF does not review luminosity or power.
It's already actually, here's an addition. It's in disclaimer, luminosity and power consumptions values have not been reviewed by ITF. So I will say a few words. Oh, it's a blunt. Okay, Steve, are you taking notes? Okay, fine. So we'll add here on this slide that luminosity and power consumption numbers have not been reviewed once again. Okay. Then we talk about this recommendation number 2, support reduce cost and energy consumption, and say that there are different concepts and they have different, I would say, behavior in terms of efficiency, luminosity efficiency at different energies, and so on and so forth. And now that's the part which we significantly tuned up. So messages and asks. Sorry?
If you return to the slide where you show ILC clip and things, I think that there is something that has to be correct or added. Not the other one. Okay, here. You have the 2 beam scheme and you put also the clustering.
Could you speak louder? Take the mask out and speak louder.
You could put the 2 beam schemes or the clustering even, because the power loss, the power is exactly the same for this. You could add it because this has been stated as one of the options that has been already made. It's not only based on that.
We didn't get your.
Okay, you put 2 beam scheme.
To what? Oh, 2 beam scheme.
Yes.
Right. And
you could add also in maybe clusters, because this is something that has been evocated in the last year.
no, what is that? The logical presentation is we briefly go through them.
No,
Time is limited. We say that there are advantages and challenges. So the challenge, if you want to change this challenge statement there, tell us what is the challenge? Is it different for click? You're talking about click, right? Right. So click. What's the challenge for click? We know that clusterance is an option.
It has been just the CERN has been asked to us this exercise. It has been high efficiency cluster developed about just to get this, and it's not only the 2 beam scheme that it has been evaluated. This means no. No, no, it has been revised, and at 380 is exactly the same. I don't know. I think that the Steiner has been put in this already. For the
How about that? We can put here in parentheses like clusterance with a question mark, saying that that's an option. It's still to be.
Option that it has been asked to us to be developed by CERN.
Fine.
We have been working it in this.
Fine. Point taken. The point is taken. The point is taken. But we proceed.
Vladimir.
Sure. Which one? I don't hear you, first of all. And second, which slide?
On this slide, I'm just curious why ILC is the last, which says ready to go, and the FCCEE, which just says supported by European. What is the order? What is the logic of this ordering? Why ILC is not first?
The logic of the order depends on, how you weight advantages and challenges. So I think from what we Tor and Steve understand, the biggest advantage of CC is not power consumption or something like that, but the biggest advantage is supported by CERN. It's part of European strategy, and it's essentially kind of a collapse of wave function. So many people believe that this is our future. That's what's happening, and that's probably what they want to hear first. Is it true? Is it? I don't know.
That's very good.
I know, but that's what CERN is pushing for.
So Vladimir, just one thing: the power consumption is not a challenge for FCC because it's only 30% more than the LHC. It's not a challenge. it is a unit of concern maybe.
Okay.
Also, if you take the energy consumption, that is a sum over the use of the machine, it is still less than the ILC.
According to
Energy consumption per Higgs is less than for the ILC.
look, that's the table. It shows 280 for FCCEE and 140 for clear for ILC and 110 for clear.
Vladimir, nonetheless, the ILC is the one project on that chart that has a fully developed technical design report. And not to put it top, really says, you really just say that the United States wants to put a knife into that project. Why don't you just say it? If that's what we want to do in the US, we should just say to Japan, we won't support it, because that's what this slide does. I think it's the thing which has the most focus and most investment by the accelerated and high energy physics communities. It needs to be first.
No.
But in any case, the number 140, I think I don't know how many mails we have to send to the ICN. We have handled it and 110. The last number. If you want,
This is taken directly from ITF report, table 1. Guys, we've seen so many miracles, like click luminosity went up, click power went down, Wakefield accelerators now the most economic ones in the world.
Copy and I will put
Okay.
copy. It's not 140, it's 110. And if you want, I will send all the numbers again.
The spreadsheet which you sent to
No,
Thomas
in the
has 140.
In the spreadsheet, we make
Okay. Fine.
just and we ask to
So what
this.
do you want us to
So
do?
Angeles, we
Concrete
will try to
proposal.
take the latest numbers that you send us, okay?
Okay.
But let me say that we spent 2 years trying to pull this together. We let people know over a year and a half ago that we wanted parameters and that we're going to have a cutoff in December of 2020.
And 2 weeks ago, we had a meeting with proponents.
Exactly. We've gotten a lot of new stuff coming in from people.
ITF doesn't want to change anything because we had a meeting with proponents 2 weeks ago. Everything was discussed.
That version of the ITF, okay, where they ask to us to make a discussion. If we want to make some comments or if you want to make some changes, we ask officially for these changes. We make all of these things. We submit it, and I don't know. I think that
Unfortunately, Thomas is not here. I don't know. Either we talk to Thomas or what. I don't know.
We will. Yes.
All right.
Thank you, Meg.
I will apply.
Yeah, can I also? I mean, I would agree that some of the things we discuss about is probably within the error bar.
Yeah.
But one thing that's not in the error bar, the presentation that was made here is the Vladimir Litvinenko's ERL linear collider. I think that should be on the list.
Why?
Not the ring-based linear collider, but the LINAC, full LINAC ERL then it should be on the list.
Okay, the logic.
ಪಾಕೆಟ್ ನೋಡಿದೇನು ನಾನು ಇಲ್ಲಿ ಸೀರಿಯಸ್ ಡಿಸ್ಕಷನ್ ನಡೀತಾ ಇದೆ.
I'm talking about the relic proposal that Vladimir presented.
Okay.
Thank you.
Thinking, I'm just saying it's not there at all.
Okay. This is the order. FCC ಇಲ್ಲ ಹಾಕಿದಾನೆ. ನಂತರ ILC. ಏನು ಶೇಖರ್ ಕೇಳ್ತಾ ಇದ್ದೇನಪ್ಪ ಕೇಳಿದ್ರೆ why not ILC at the top, FCC next?
Where's the microphone? Tor, say something. You know. Where's the microphone?
We're gonna, Angeles will deal with your suggestion. You know, but thank you. And let's move on.
So ITF takeaway will be modified, and we'll add once again that we didn't review power consumptions and luminosity numbers. Okay. We show that slide, and then we proceed to accelerator messages and asks. Okay, and that's where some new slides coming up. So the first slide is that we hear the message from the community. That community believe that we need new ideas to come in. For example, from John's Hewlett's talk Sunday, this slide shows that the vision of previous P5 is significantly progressed compared to P5 itself. So this is year 2015, that's where we are now. And if in the past, there were many ideas and many proposals, and we sort of implemented many of them. So that's what's shown in the green and blue. We either finished them or and operating them or finishing construction of those, but planning for the next decade. So the proposals for the next decades in yellow, we see less and less of them. So the point is that we see how few new proposals are in the system are under consideration right now. And the message from Accelerator Frontier is that we have a broad array of accelerator technologies and expertise to design and construct prioritize HEP accelerator projects for either neutrino physics, rare processes, physics, or energy frontier. Now, second message is that regarding the colliders, so we need an integrated future collider R&D program in the Office of High Energy Physics to engage in the design and coordinate the development of the next generation collider projects. So that program will allow us to address in an integrated fashion the technical challenges of promising future collider concepts, particularly those aspects of accelerator design technology and beam physics that are not covered by existing general accelerator program. That program, that initiative, will enable synergistic US engagement in ongoing global efforts such as FCC, ILC, and International Muon Collider, and develop collider concepts and proposals for options feasible to be hosted in the US, like C-Cube, Helen, Muon Collider, etc. So the slide in support of that statement of the need of that facility is shown here. So if you look into the official HEP Advanced Technology R&D budget in the previous 10 years, you see that we originally started 10 years ago in 2012, fiscal year 12, at approximately $130 million. And that budget steadily went down, but most drastically and most visible is the disappearance of that red bar. And that red bar corresponds to the so-called directed R&D. So gray is for facilities, operation and construction, beam facilities, test facilities. Blue is general accelerator R&D, and the red bar was for directed R&D. And that includes things which we completed eventually by around 2016, 2017. So we finished our involvement and contributions into ILC. We finished our contributions to LHC in the form LHC research, in the form of LHC accelerator research program. We kind of reassessed and eventually closed so-called Muon accelerator program in the US. And that's what was in this red bar. So right now, we don't have focused effort on future colliders whatsoever in the portfolio of high energy physics. And the proposal, can you take this closed caption? It interferes with everything. So I don't know whether we should cut it off completely. So the proposal is that in the next 6-7 years to reestablish this investment into directed R&D and which will be focused on the future colliders. So I don't show these bars. These bars don't indicate exact numbers, so those to be defined by P5. But now, after you've done something, you click again on the screen because otherwise this slide changer doesn't work. Right, and again, this. Okay. Exactly, it's extremely annoying. Right, so and that's what the integrated program focused on future colliders will do. So basically, that will allow us to look into the international options on the US soil, in the US and abroad, and design and research and development can be supported out of this new program.
Can you go back one slide, please? Can you go back one slide? One more slide. So I am just wondering whether there's a way to have an integrated future for collider R&D instead of being completely guard specific or add a bullet about NSF or something so that it's just not. You wanted to include NSF? Yeah, maybe. So
so we talk a lot about an integrated future collider R&D program in OHEP, but some kind of recognition of NSF participation.
Maybe slash NSF, Sergey. Is it okay to put NSF here? Oh, basically asking in general community.
Snowmass is a
They're asking P5 to make a recommendation.
It's a joint DOE NSF activity. It should be there.
Sergey says, why don't we just remove funding agency naming? Good point. We'll address it.
Thank you.
We will not take out the guard because that's in your proposal. That's a language from initiative. Okay, so well taken. So message number 3. So regarding research and development, accelerated research and development, what is N? I don't know. Steve, please take a note. We have an ongoing R&D program aimed at fundamental beam physics. I don't know what N means, and long-term level of accelerated concepts and technology. No. Something that's it's an action item. We propose or we support. It's again obvious typo. We have an ongoing R&D program. Okay, so it's slide 49, 43, right? Aimed at fundamental beam physics and long-term level of accelerated concepts and technologies, SRF, magnets, beam physics, etc. So this R&D will be focused in the next decade on reduction of environmental impact, power consumption, and it should be pursued. All these items have broad applicability across Office of Science. And in general, we believe that R&D is key to our main messages regarding the facilities. So future facilities require significant R&D. And key message number 2, that's our message on colliders.
Vladimir, in your etc., I know you have that there, but why don't you explicitly say something about computational physics? I mean, we can't do anything without that.
Isn't that part of beam physics?
Yeah, well, no, it is part. Yes and no. Beam physics means, we can't even get funding for guided study instabilities.
There is slide next 44 that includes for accelerated beam physics that we plan to develop new complex computer modeling and explore new AI ML approaches.
That's fine. That's fine.
So this Tor, Steve, the language is blurbed here, so the word is lost. Okay. I don't know. In comments, should we add anything or not? What is missing? We have an ongoing. Right. No, it's a message. Essentially, we are telling the community that's.
Oh.
Steve, are you taking notes? Okay.
Going to Richie's point, you say broad applicability across the Office of Science. Should something be said about NSF in that?
Yeah. Yep. Oops. Yeah. So mention and then we should mention targets and sources. Okay. Because next slide is exactly about that. So we go through all these, 5 major thrusts one by one. And again, each thrust will be represented by essentially what we do over the next decade, approximately, and what's now plan, right? So for targets, the targets for 2.4 megawatt PIP3, and potentially look into how we can build much higher power targets for muon collider, for magnets and colliders, and magnets for colliders and RCS is a bunch of dipoles, solenoids, fast cycling magnets, and that should be and will be coordinated with the US MDP. Then again, this annoying capture, closed caption should be removed. I know where to go. That's the slides are so dense right now. It's there's just no space for anything. Can you turn it off? Is it okay? Or audience will complain if you turn it off. Right. So basically, you see there are multi-megawatt targets, magnets for colliders and RCSs, rapid cycling synchrotrons, superconducting, normal conducting RF and wave fields. I hope that major bullets are okay. If not, tell us right now. So again, understand there should be like 3-word sentence. That's here. Accelerator and beam physics becomes sort of overarching, right? So it's the last of the thrust we mentioned.
Quick comment here, Vladimir. The 4 to 8 megawatts for a muon collider, I don't think we've been talking about numbers quite so high. I think we've been successfully keeping it below 4 megawatts, maybe closer to 2.
Concrete proposal, what should the number be?
I would probably say 2 to 4.
Mark Palmer says that it's 4 to 8.
I trust Mark Palmer then.
Okay. So let's stick with 4 to 8 megawatts for magnets. Is it about right?
Vladimir, Sasha Zlobin.
Yeah.
I think we should increase number for solenoids to at least 40 Tesla.
Okay, 40 Tesla scale, and this one, about right? About right, okay. That's not wow. Again, AF7 guys, are we dreaming of 20 Tesla dipoles, or 16 is enough? No, point is that they have their own, we're sort of summarizing what our topical groups.
Yeah. Vladimir, it depends what you mean by that number.
I would stick with 16.
I mean, that's the operating field. That's the operating field on center.
Plus, we should probably distinguish when we are talking about arc magnets, and obviously 15, 16 Tesla, that's a reasonable nominal number, taking into account technology and cost. But for example, for IR magnets, we could talk about 20 plus Tesla, keeping in mind both dipoles and quadrupoles.
Okay, so what I hear is that 40 Tesla is the only change. The rest stays as is. For RF, AF7 RF, is it about right? 7,220 megawatt per meter C cube type, and 72. I don't know where I got number 72. Sergey said it should be 70.
72 looks awful specific. And it's no different. It's no different from 70.
You know what? The whole logic here is to show how relevant we are. So again, it's not that we specifically do it for something, but potential users, end users, are sort of listed here, like muon collider, RCS. So you're saying here we should kind of, that's good? No, 72 or 70 plus. It's good. 70 makes more sense. Let's make it 70. Sergey B also told me that. Let's change it to 70. New materials, high quality factor cavities, and efficient RF sources. About right? About right.
Yeah.
And wake fields, what do we say about wake fields? That their focus for the next decade is to explore collider quality beams, accelerated in plasma and structures, explore efficient drivers, and work in close coordination with international initiatives such as those proposed by European Roadmap, Eupraxia, and others. Wrong, right? Is about right?
It misses the high repetition rate.
Efficient drivers and staging.
Luminosity.
Okay, then Steve.
But I don't know whether you want to, you can't put too many things on the slide.
Okay. And then as a final message is that overarching importance is accelerating beam physics. And over the next decade, the focus of these explorations will be on high intensity, high brightness beams, acceleration of such beams, control of such beams. Sergey? New complex computer modeling and energy efficient design options.
Then maybe there was a suggestion to actually list our 4 grand challenges instead of these 3 bullets.
Sergey, we have space for 16 words. So if you put 4 challenges.
Well, 4, I mean, they are, we know them. They are, intensity, brightness, control.
I have word intensity, I have brightness, I have word control. Maybe that satisfies. You see, along the same lines as other guard thrusts got, very.
Okay, let me take a picture of it. I'll think about it.
Okay, think about it.
Thanks.
And again, if you send something before end of the lunch, would be best.
Vladimir, do you intend the word control to include all of the issues included in machine protection as we get to higher and higher stored energy, higher circulating power, and so forth?
Bill, the answer is yes. The word control has a lot of meanings, but for the audience which will be in front of me, it would mean essentially nothing. So 80% of them are cosmologists and collider folks. So they.
I got you.
Okay, so frontier message number 4. So in terms of workforce, we need to strengthen and expand education and training programs in the US. We need more research grants to involve professors in DOE lab facilities and projects, strengthen US particle accelerator school. Labs need to accept more traineeship students, including international ones. In terms of outreach, we want to enhance recruiting, carry out an extensive program of colloquia at universities, and in terms of diversity, equity, and inclusion. So we plan to enhance support to national undergrad recruiting class to bring women and underrepresented minorities talent. Yeah, Cameron.
This is nice. The right now has the review call out. That we might add to the last bullet and MSI institutions.
Can we somehow work together to tune up language of that particular slide? So
yeah, one comment, the need for a recruiting class isn't, I think, specific to only women and URMs. However, Fermilab is under renew. They're talking with me now, and they're trying to write a proposal to get a recruitment class going.
Steve, don't talk about details. Question is, what is our message? What do you want to tell these 700 people?
Get a recruiting class.
That's what's
right
there.
But it reads as
okay. Fine.
One thing you need is strong funding for university-based research.
Strong funding for university-based research. Somehow we need to plug it in, okay, into this text.
Yeah, I mean, the fact is, if you don't get to catch students into programs at the university, recruiting programs are going to fish in a very, very small pond.
Okay.
You got to make the pond bigger.
Okay. Done with this slide. Next one is. Yeah, how do we bring? Actually, NSF is consistently missing our in this slide so far. I don't know. Just.
I think the intent there is actually DOE labs. We want to involve
thing before that, which is just strong funding for university.
Yeah.
resources.
I
Yeah.
think that's an important
And that
addition.
could come from the NSF and DOE.
Yeah.
From NSF and DOE, Steve. Research
Funded
grants from
university programs. I mean, that's a key.
Okay. Last message is that accelerated development should be part of P5. We strongly believe that planning of accelerated R&D should be aligned with strategic planning for the high energy field of high energy physics, and should be considered as part of the P5 prioritization process. So last time we didn't see that, so we have separate processes for accelerators and for the rest of high energy physics. This time we strongly believe that to be effective, accelerators should be part of P5 process.
Mark?
So the only question I have about this message is that if we say it in a way where it's really tied to expected needs of HEP, we might narrow the R&D aspects of this somewhat. So can we perhaps rephrase it just a little bit to avoid that?
Like what, for example?
So it needs to say that there needs to be
planning
direct-
of accelerators. How about that? Planning of accelerators
Planning
rather than
of
just R&D.
Yeah, so the R&D needs to be a little broader than tied strictly to HEP needs, because we need to plan for future needs that will appear. And so that's, yeah, it can just be too tightly interpreted.
Okay.
Jeroen and Georg. So we need concrete proposals.
Could you explain a little what you mean? It was not the case last time. Many accelerator proposals since the last P5 ask explicitly for relevance to P5 priorities.
Yep.
And the P5 panel did consider readiness, accelerator readiness of the proposal. So I think the accelerator was already tied in last time.
That I think you captured the idea correctly. So that since previous P5, we see more and more of disconnect between what HEP facilities want and what HEP guard does, or R&D. So that should be united again, one way or another. Question is how we, first of all, we shouldn't bullshit previous P5, right? So, and the second is that we should correctly state what exactly we mean. So Darren, please tell us, maybe you know kind of better way to say that.
Thank you. I think in addition to all the priorities and the roadmap, that's fine. I think two messages I think important to our field. One is no further cut of our R&D.
Okay.
Second, we need to ask for increase for the R&D accelerator general. Somewhere the message need to be reflected some way in the P5 report, because that has been the case for the last decades.
That actually belongs here. So,
okay.
But basically the strengthening of R&D.
How do we want to emphasize the 2 points, right? Because it cut to our bones, so painful now.
Yeah, Vladimir, just
after seeing this plot,
yeah,
people can easily conclude that yes, that should be stopped. Yeah, indeed, Steve, maybe somehow that strengthening R&D support seems to be critical, because we are looking into the new era of new facilities, and we are not that prepared so far. Okay. Back to slide number 5, message number 5. Sorry. Is it about what we want to say, Georg?
So Vladimir, why do you say for the HEP field? Why not just for OHEP and NSF?
Oh, HEP means here high energy physics or particle physics. Planning for particle physics. Maybe instead of HEP field, the strategic planning for the particle physics and be considered as part of P5 prioritization process. How about that?
After all, the stewardship is still considered, at least in the Office of Science, part of the OHEP mandate.
You missed the point. This time we want to be part of P5 process. Basically, P5 shouldn't leave it.
I understand that. I understand that.
So, Steve, how about if you remove HEP field and with a substitute with particle physics, planning for particle physics? Yeah,
particle physics, actually, yeah.
That's exactly the point.
I was a little more precise the way you said it.
Yeah,
Yeah.
so fully agree with that. And I want to second Darren's point and advocate that it be, it's important that it be part of message 5, but I think that it should also be the message on which we end on this slide. So I'd like to advocate that at the top of that slide, essentially, I think we should try to motivate to the particle physics community, why should we be part of P5, right? So we advocate that clearly, right?
How?
But I would advocate at the top of this slide, we could have a bullet that would say something along the lines that accelerator technologies are rapidly advancing and provide multiple options to provide the needs of high energy physics. Could list neutrinos, TeV and T beyond, and that collider development is needed to address that, right? So I think we should, in other words, have a motivation of why.
Cameron, I think that's a good idea, actually. We can have.
But more concise. It all should be said in like an
Yeah, I
one,
think
one short
I agree with
sentence.
you. I'm trying to
I
phrase
completely
this, but-
agree with this sentiment. But I believe what Mark said is important, that this should not sound as if all accelerator R&D has to be following the priorities of P5. That's not what we want to say. So I would keep it short like this, but I would remove planning of accelerator R&D should be aligned. I would take that out. I would just bring across only the point that we believe accelerator scientists should be part of the P5 prioritization process.
Yeah, we don't want to be aligned. We want to be part of the strategic plan.
Right.
I also want to follow up a couple of the comments. If we say here specifically for particle physics, or you call it GP, are we creating the silo situation in GARD completely to future collider or proton driver, or how do we pick up the topics that are cross-cutting? That's my concern.
You know what? SNOMAS is supposed to be fluffy and all-inclusive. Right now, we kind of don't create any silos. We basically emphasize points of importance. Detailed planning, it will take probably a year or two, right? But definitely all roadmaps will be updated one way or another. So, what we're asking is that maybe priorities for R&D or general priorities, basically all these considerations for what needs to be done in terms of accelerators, be part of P5 consideration process and prioritization process.
I think part of the issue here is that when we talk about accelerator R&D, we're thinking just the HEP portion of the accelerator R&D, but people are thinking, well, when we say this, it's much broader than that. And so we need to think of a way to rephrase that.
Oh,
And I think Richie had a very concise way of saying this, which somehow I can't remember. So maybe you want to try it one more time.
I think it's something like accelerator R&D should be incorporated into the P5 planning process.
that's what we said.
Yeah.
Or should be incorporated, instead should be aligned. So should be incorporated in the P5 prioritization process.
Yeah.
Yeah.
Make sense? Makes
Yeah.
sense. Okay.
Yeah.
It's Richie. Okay.
I had a suggestion, but she had a better one, so I see.
Okay.
Yeah. So you don't even need for the HEP field because the
No, that
P5
will be
I think we got it, Bill.
particle physics or whatever. So,
yeah.
and the rest will be like, thanks for your attention and so on.
Yeah.
46 slides,
doing-
it'll
how
take
we
about
doing
50 minutes, 55 minutes.
So
Is it incorrect?
No, I think the room is a private company. They made a ton of money.
Fine,
And-
supposed to be joke, but I was told, don't joke, Vladimir. Leave the joke. Okay, leave the joke. Okay.
But
I doubt I will have time to even to read it, and they just say that we thank so many people who took part in this extremely useful and long and exercise.
So Vladimir, did we lose the point that Jérôme made that we can't really stand further cuts?
Bill, say that again.
You know, Jérôme made the point, we can't stand further cuts because what we've seen is a decade of cuts. And we can't stand that. And if we have further cuts, this will damage the vision of facilities for high energy, for particle physics. Or somewhere we got to say that. That's what I think Jérôme was pleading for. And I think we missed that thought.
I'm not know where you want to put it, but I think it ought to be clear to,
I think we can emphasize that the field is squeezed in the plot that Vladimir shows about the funding. And you can simply
Okay.
make a statement.
I mean, it just has to make clear that it just jumps out at people, whether you say the words or not.
Scott, did you have a comment?
Yes, yeah, and it really kind of goes back to yesterday's iteration of this. So, and also to one of the earlier comments here. So the way you gave the talk, at least, and I don't know if this was your intention necessarily, tended to put a very, I'm going to say, positive spin on FCCEE in the sense that you seem to give the impression that there was a very large probability that it was something that was going to eventually go through. Now, maybe you didn't intend that, I don't know, but that was certainly the impression that I got. And when, if you give that impression, then the next logical question that comes up is that if you do FCCEE, now you're now essentially you've changed the landscape because now you have the big tunnel, right? And now FCC HH now starts to become highly probable, basically. So mostly I'm saying I think you should address that in some way in the way you're presenting things, whatever, because that was certainly something that stuck out to me. Anyway, that's it.
So I don't think we're prioritizing anything in this talk, and that's not the intent.
No, you may be right. I'm just saying it did come off that way to a certain extent in some of the earlier slides. And I mean, this was rehashed here to a certain extent based on that one slide, but I don't think that's the only place where that impression was given, basically.
Can I make a comment? If you don't prioritize, but just use the alphabet, then you don't have rank anything. So,
there is no ranking.
Right. So then basically you use the alphabet. Because the letter comes first or second, and that then it's kind of which one comes first. Then.
Yeah, again, I don't think this was something that I saw in a specific slide, but I think if you it was either, I don't even know if it was on the content of the slides, but it was the way they were being presented. It was the idea that it was the impression that FCC had a very high, FCCEE had a high chance of going forward because it was a CERN project, et cetera. It was those kinds of comments, I think, that can give that impression, basically. So it sounds like that wasn't the intention, but
You mentioned FCC here on the third sub-bullet.
it was specifically FCCEE, and it was early. It appeared earlier on in the talk in a couple of instances.
Yeah, it was in your list of Higgs.
Those are the slides from yesterday.
Yeah, exactly. But it's these slides, basically, right? If I understand, unless I'm confused, which is entirely possible. But yeah, it was. This is a holdover comment from yesterday, which I did not get a chance to give, basically.
Yes, here.
Yeah, that one.
Okay. May I say the logic? So maybe you should understand the logic. Logic was, we as Accelerator Frontier, we got input from Energy Frontier and 4 different entities. Energy Frontier message is extremely crispy clear that Higgs factors are priority. So, and there are 1, 2, 3 Higgs factors we specifically mentioned here as mature ones, or matured, right? And we talk about them. The order, whatever, you can argue about the order, whether citing FCC first means something. I don't think so.
Not the intent, but a number of people are saying that.
Yeah, it wasn't an impression I got from the order. It was the impression from how it was described, basically. The words you said, I think. That's kind of what I'm getting.
Hey, Vladimir.
Yes, please.
I got a very naive question on the bar graph of the funding. One could, without having the full history, one could naively say that there was an intentional bump to address funding of some critical items. And as those items came off the list, funding went back to some normal funding. You know, the bar graph you have with ILC and a MUON MAP program. So I naively say, oh, we had a decade of decrease in funding, but could people come back and say, well, what was the other one? This one here, say these directed funds were there intentionally to bump up this program we wanted to address.
Right.
Those come off the books now back to this funding. So if you don't have a directed R&D that says we need these particular items, could they just say, we're back to where we were?
LARP finished. It's true that LARP finished.
Historically, actually, the
ILC funding
funding was up for about $140 million in 2007. But we don't have the information right now. And so we'll leave this as is, but I think, spinning it this way is useful. Let's see, next, I'll ask.
Yeah, I think the possibility that the FCCE goes forward is what it is. It's non-negligible and it's good. I don't think you want to kill it.
No, I don't.
But there is a possibility that it doesn't. But in any case, the R&D program should be modulated it will be different in one case or the other. And that is not indicated in what you said. Okay. Now, this answer is likely to come in a few years and maybe at the very beginning of the next exercise, between 25 and 27. So I think it might be worthwhile considering a separate little exercise that says, how does this project on one scenario or the other? And there's one thing I can tell you, the FCC does lots of wonderful things. The FCCEE is justified in its own right. But there's one thing that the FCC program will never do is a high energy lepton collider. And so for instance, the MUON collider development is something which is absolutely not affected by that decision. Okay.
Yes and no, because if you have a high energy proton-proton collider on the horizon, which you probably would if you built FCCEE, does that not, from the point of view of the high energy physicists, say, oh, we're going to use that rather than building a MUON collider?
The physics of MUON collider and hadron collider are not the same. And even in the FCCHH scenario, if there are discoveries made, you might say, I really want to have a MUON collider to back it up. So for instance, the energy range of the Higgs factories we're talking about is lower than the LHC, and yet there was a discovery at the LHC that makes the Higgs factory very important.
Wait, stop. Okay, we're not debating here. We're not prioritizing.
Right.
And we're trying to avoid prioritization. So this has come off as something we can fix this. Perhaps we'll do this by putting ILC on the top. Just
And there's
could you go back to the budget page again? Just I wanted to address because I thought it did.
While we do that, I've got it.
You got it.
Is this the right direction?
No, but yeah, I think you're going in the right direction. But what I wanted to follow up on Bill's just because I think that page probably does confuse a lot of people. So I guess that first big drop was when the ILC got.
No, the ILC was killed in 2008.
Okay, so that I'm not sure, but a lot of that in between was LARP, and that is now the significant parts of that have rolled over into project funds for HLLHC. So that didn't go away as such, but it came down. And the other, I would guess, was when some part of the drop was when the lion's share of that was LARP from like 2013, for a lot of that time.
2012 to 2013 was LARP, and then the rest was really MAP.
Yeah, then MAP got kicked to the curb by the last snowmass. So that kind of explains that. But yeah, so LARP. Yeah, so LARP, a lot of that was LARP going away, but it hasn't actually gone away because that has gone into projects.
Right.
Okay.
That was the goal of LARP.
Yeah, I'd like to point out that the presentation is still fairly unbalanced with regard to
left-hand colliders at the 10 TeV level. We all know that there's two approaches, muon collider, Wakefield colliders. And particularly above 15 TeV, there may only be one option, Wakefield colliders. And
there were no options.
you know, all week long, you've been asking us the tough questions. What's actually been experimentally demonstrated with Wakefield colliders? You're pointing out over and over to us in many orders of magnitude. I think Vladimir's quote was countless orders of magnitudes difference between what's been demonstrated experimentally and what's been what you need for a collider. But we don't hear those same type of questions about the muon collider. But if you ask the question, what's been demonstrated in terms of muon beams, not only muon beams, anti-muon beams, in terms of beam parameters, the energy that's been demonstrated, the acceleration that's been demonstrated, energy spread, emittance, and ask the question, how many orders of magnitude are you away from that reality, experimental reality, and what's needed for a collider? You're going to find there's countless orders of magnitude, many countless orders of magnitude. And why is this important? In the standard definition of technical readiness level, this gap between state of the art, what's been experimentally demonstrated, and what's needed for the application, that is the fundamental factor that goes into determining the technical readiness level. And if you look at that definition of where we are experimentally to what's needed, you're going to find Wakefield accelerators are favorable compared to muons in terms of what's been demonstrated experimentally as in terms of the actual muon parameters. So I'm just advocating when this list comes up for 10 TeV options for the left-hand colliders, Wakefield accelerators should be on there. In addition to muons. And there's several places in this report where that's just not the case.
We've heard that message several times, but follow the logic so far. We start with what energy frontier wants. And there is specifically mentioned Higgs factories and multi-TeV muon colliders. Then we present, just a second, let me finish. Logic of this presentation. Then we have 4 other inputs. One of them is plus A minus collider input, which is kind of good in favor of whatever 10 TeV or 15 TeV. Then we have mu plus mu minus for muon collider input, which says there are no showstoppers. Then we have implementation task force, which is extremely positive about muon colliders. And you want us to put everything kind of in the same unsorted fashion and brought it to the community. Basically, you decide what to do. I know that's one approach, but again, so far we decided just follow what people said. In some sense, we wait by community. And we clearly understand what you want to say, what you want to see here, but it doesn't fit the logic of this frontier.
So Eric, I think from my point of view, the challenge that we have here is that people have done a lot of work mapping out, no pun intended, mapping out how you would get to a multi-TeV, 10 TeV scale muon collider. And we don't have that for the plasmas that I've seen. And so
we have a rough map, but there is still reality.
The roadmap doesn't.
The reality
roadmap
is
doesn't help.
what has been
It's understanding the
experimentally.
physics challenges of where you are. And so if you can show that, and you've got P5 is going to start up in a few months. You've got time to develop that case by November. We had asked you for that multiple times leading up to this, but you've got time to develop it for the November P5 and just show them, hey, we can reach 15 TeV. Here's all the physics. We've got totally self-consistent parameters. That would be great. But again, I think right now we need to understand, we don't see that path.
Sorry.
I think you're doing the community a disservice by excluding Wakefields from the 10 TeV
So
lepton.
I think we
collider.
do want to think about how to get something from there. You're right. Cameron?
Great, thanks. So, I certainly want to acknowledge the fantastic work that's been done by the muon program, right? The muon collider report is really nice. I think, I think that what to me would be appropriate is, when you have not necessarily expressed interest, right? But, now it's our turn as an accelerator frontier to come back and say, hey, here are the options, right? So for example, Sunday we'll have a session on the integrated, collider program, right? That'll include Wakefield accelerators, which is great. And so, for example, on the lists on this and the next pages, I think it would be appropriate to, at least in 1 or 2 of those locations, to find a way to acknowledge that future possibility, right? Such that we, I think there's a balance here, right? Between acknowledging that work that you're talking about, right? And also finding a way to present the community, right, with all the options. So
So let us take some time during lunch, I guess, and see whether we can incorporate something in there, okay?
thank you,
Or
much
just get
appreciated.
Presented to the larger group.
And for your reference, I put a couple of those suggestions in the document just so you have them for consideration. Much
Okay.
appreciated.
Let's see, we are going to be kicked out of here in a few minutes, so let's get a few more comments and then we'll have to move on. Or move out.
Oh, Sergo.
Sir,
So maybe a quick clarification. One thing that I think made the difference in the Muon Collider Forum report is the fact that we, with respect to the previous P5, on the experimental side, on the side of a detector, we came up with a concept of a detector where we convinced ourselves that with reasonable extrapolation of a technology, we had a specific design and we can do high quality physics with this. And I think I mentioned this before, I certainly encourage the wake field. It was said multiple times in the past, assuming that the beam conditions are exactly the same and that you can place your detector in a way that ensures the same efficiency and acceptance, you can do physics to first order. It should be flavor agnostic. So I think we encourage your community to do the same and came up with the same the same basically proof of concept. Essentially, that would certainly help. The other comment, I think I wanted to address what Scott said, also from the EF point of view. I think I fully agree with Alain that the physics program of HH machine and Mu machine, even though they have overlaps, they're not exactly the same. And we will learn in the next, let's say, X number of years from the Higgs factories, as well as from precision experiments. We may learn about the hints for new physics and where to look for it. So I think in that sense, it makes a lot of sense for the future for R&D for the future machines to continue. And so maybe that's the message that needs to be made, and not try to prioritize on this hadron versus high energy lepton machine at this point.
So from the accelerator frontier, we're not trying to prioritize on.
Yeah, that
any
was
of these things.
poor choice of word, not prioritize, but not to say that one should be, well, I guess dropping one. means-
So we mentioned the Muon Collider a number of times, but of course, for the hadron machine, it's magnets. And we mentioned that R&D program.
Right. No, I think it was Scott's comment that prompted me to say this. So I think that gets reflected in the presentation. That's perfect.
I think we're eating time of lunch now.
Anything else? Chico.
This is just a minor comment, but it's to the first takeaway message. It stated that the ITF reviewed concepts. And I think that's a slight understatement. Perhaps it could say something more along the line that it was a comprehensive review, because it is a reference document for the
Wrong
rest.
direction.
So this is E5. And then the first
Oh, there was a statement somewhere about what the ITF did, just simply stating that it reviewed concepts. I think it. that
Oh,
statement
it was
could
a
be-
message about ITF takeaway.
Yes,
Yes,
strengthen.
way up. Yeah, here, back. Yes. Right. So, and you
Yeah, I
like
think,
it?
yeah, it should be rephrased to say that it provided a comprehensive review of all these options and
Oh, it is set on the slide where I introduce implementation task force.
okay.
Go a few slides back. You see that yes, here. That's in there. It will be said at least. And the word comprehensive later will be kind of augmented by disclaimer that it's not comprehensive. We haven't looked. We haven't looked at the power consumption and luminosity numbers, which have many of them have enormous risks, as Eric correctly pointed out.
Okay. Going once. Going twice. Session closed. Thank you all.
Thank you.